1. Introduction to computer graphics. 1.1 Overview of computer graphics. Computer graphics is a field that deals with the creation, manipulation, and rendering of visual content using computers. It encompasses a wide range of applications, including video games, virtual reality, animation, simulations, and visual effects in movies. In order to create realistic and immersive visual experiences, computer graphics relies on various techniques and algorithms. One important aspect of computer graphics is optimization, which aims to improve the efficiency and performance of rendering algorithms. 1.1.1 Frustum culling. Frustum culling is a technique used in computer graphics to improve rendering performance by eliminating objects that are outside the view frustum. The view frustum is the portion of the 3D scene that is visible to the camera. By removing objects that are not visible, the rendering workload is reduced, resulting in faster frame rates and improved overall performance. The frustum culling process involves determining whether an object's bounding volume intersects with or is contained within the view frustum. A bounding volume is a simplified representation of an object's shape, such as a bounding box or a bounding sphere. By performing simple intersection tests between the bounding volumes and the frustum, objects that are completely outside the view can be quickly discarded. There are several algorithms commonly used for frustum culling, including the axis-aligned bounding box AABB test, the oriented bounding box OBB test, and the sphere test. The AABB test involves comparing the minimum and maximum coordinates of the bounding box with the frustum planes. If any of the box's corners are outside the frustum, the object is culled. The OBB test is similar, but takes into account the object's orientation. The sphere test checks if the object's bounding sphere intersects with the frustum. Implementing frustum culling involves traversing the scene hierarchy and performing the intersection tests for each object. This can be done using various data structures, such as spatial partitioning schemes like octrees or bounding volume hierarchies. By organizing the scene into a hierarchical structure, the traversal process can be optimized, reducing the number of intersection tests required. When implementing frustum culling, there are several performance considerations to keep in mind. The accuracy of the bounding volumes used can affect the culling results. Tighter fitting bounding volumes can reduce the number of false positives, objects incorrectly culled, but may require more computational resources to calculate. The complexity of the scene and the number of objects in the view frustum can also impact performance. Efficient data structures and algorithms are crucial for achieving real-time frustum culling in complex scenes. Frustum culling is an essential optimization technique in computer graphics, as it allows for efficient rendering of only the visible objects in a scene. By eliminating unnecessary rendering operations, frustum culling significantly improves the performance and responsiveness of graphics applications. It is widely used in real-time rendering systems, such as video games and virtual reality applications, where maintaining a high frame rate is crucial for a smooth and immersive user experience. 1.2 Graphics Pipeline. The graphics pipeline is a fundamental concept in computer graphics that describes the sequence of operations involved in rendering a 3D scene onto a 2D display. It encompasses various stages, each responsible for a specific task, such as transforming 3D objects into 2D coordinates, applying lighting and shading, and finally rasterizing the scene onto the screen. Understanding the graphics pipeline is crucial for optimizing the rendering process and achieving real-time performance in computer graphics applications. 1.2.1 Overview of the graphics pipeline. The graphics pipeline can be divided into several stages, each contributing to the overall rendering process. These stages include vertex processing. In this stage, the 3D objects in the scene are transformed from their original coordinates to a common coordinate system known as the world space. This transformation involves operations such as translation, rotation, and scaling. The transformed vertices are then passed to the next stage. Primitive assembly. In this stage, the transformed vertices are grouped into geometric primitives, such as points, lines, or triangles. These primitives form the basic building blocks of 3D objects and are used for further processing. Rasterization. In this stage, the geometric primitives are converted into fragments or pixels that will be displayed on the screen. The rasterization process involves determining which fragments are covered by the primitives and assigning attributes such as color and depth to each fragment. Fragment processing. In this stage, the attributes assigned to each fragment during rasterization are processed further. This includes operations such as applying lighting and shading models, texture mapping, and blending. The resulting fragments are then ready to be displayed on the screen. Output merger. In this final stage, the processed fragments are combined with the existing frame buffer, which holds the current image being displayed on the screen. The output merger stage performs operations such as depth testing, alpha blending, and stencil operations to determine the final color and depth values for each pixel. 1.2.2 Frustum culling. Frustum culling is a technique used in computer graphics to optimize the rendering process by eliminating objects that are outside the view frustum. The view frustum is a truncated pyramid-shaped volume that represents the portion of the 3D scene visible from the camera's perspective. By discarding objects that are not within the view frustum, unnecessary computations and rendering operations can be avoided, resulting in improved performance. 1.2.2.1 What is frustum culling? Frustum culling works by determining whether an object's bounding volume intersects or lies completely outside the view frustum. The bounding volume is a simplified representation of the object's shape, such as a bounding box or a bounding sphere. If the bounding volume is found to be completely outside the view frustum, the object can be safely culled, as it will not contribute to the final rendered image. 1.2.2.2 Frustum culling algorithms. There are several algorithms available for performing frustum culling, each with its own advantages and limitations. Some commonly used algorithms include axis-aligned bounding box AABB test. This algorithm uses axis-aligned bounding boxes to represent the object's bounding volumes. It checks whether the bounding box intersects or lies outside the view frustum by comparing the coordinates of the box's corners with the frustum's planes. Sphere test. This algorithm uses bounding spheres to represent the object's bounding volumes. It checks whether the sphere intersects or lies outside the view frustum by calculating the distance between the sphere's center and the frustum's planes. Oriented bounding box OBB test. This algorithm uses oriented bounding boxes to represent the object's bounding volumes. It takes into account the object's rotation and checks whether the bounding box intersects or lies outside the view frustum by transforming the frustum into the object's local coordinate system. 1.2.2.3 Implementation of frustum culling. Implementing frustum culling involves performing the necessary calculations to determine whether an object is inside or outside the view frustum. This typically requires transforming the object's bounding volume into the same coordinate system as the view frustum and performing the intersection tests described in the previous section. The implementation can be done on the CPU or the GPU, depending on the specific requirements of the application. 1.2.2.4 Performance considerations. Frustum culling can significantly improve the performance of a graphics application by reducing the number of objects that need to be processed and rendered. However, it is important to consider the trade-off between the cost of performing the frustum culling calculations and the potential savings in rendering time. The complexity of the object's bounding volumes, the number of objects in the scene, and the frequency of updates to the scene geometry are factors that can affect the performance of frustum culling. It is essential to profile and optimize the frustum culling implementation to achieve the desired performance gains without introducing unnecessary overhead. 1.3 Rendering techniques. Rendering is the process of generating images from a 3D scene using computer graphics algorithms. It involves transforming geometric models into 2D images by simulating the behavior of light and materials. Rendering techniques play a crucial role in creating realistic and visually appealing graphics. In this section, we will explore some fundamental rendering techniques, including frustum culling and occlusion culling, which are essential for optimizing the rendering process. 1.3.1 Frustum culling. Frustum culling is a technique used to determine which objects in a 3D scene are visible within the camera's view frustum. The view frustum is a truncated pyramid-shaped volume that represents the portion of the scene visible to the camera. By eliminating objects that are outside the frustum, we can significantly reduce the number of objects that need to be processed and rendered, resulting in improved performance. The frustum is defined by 6 planes: near, far, left, right, top, and bottom. Any object that lies completely outside any of these planes is guaranteed to be invisible and can be safely discarded. To perform frustum culling, we compare the bounding volumes of objects, such as axis-aligned bounding boxes or bounding spheres, with the frustum planes. If the bounding volume is entirely outside any of the frustum planes, the object can be culled. There are various algorithms for frustum culling, including the bounding sphere test, the axis-aligned bounding box test, and the oriented bounding box test. Each algorithm has its advantages and trade-offs in terms of accuracy and computational complexity. The choice of algorithm depends on the specific requirements of the application. 1.3.2 Occlusion culling. Occlusion culling is a technique used to determine which objects in a 3D scene are occluded or hidden from view by other objects. It aims to reduce the rendering workload by excluding objects that are not visible due to occlusion. By avoiding the rendering of occluded objects, we can achieve significant performance gains. Occlusion culling involves analyzing the scene's geometry to identify occluders and occludees. An occluder is an object that blocks the view of other objects, while an occludee is an object that can be occluded. The occlusion culling algorithm determines which occludees are completely hidden by occluders and can be safely culled from the rendering process. There are several occlusion culling techniques, including the portal-based approach, the occlusion query approach, and the hierarchical occlusion map approach. The portal-based approach divides the scene into connected regions using portals, which are openings between different areas. By determining which portals are visible, the algorithm can determine the occlusion relationship between different areas. The occlusion query approach uses hardware-accelerated occlusion queries to determine if an object is visible or occluded. This technique leverages the graphics hardware's ability to perform occlusion queries efficiently. The algorithm queries the graphics hardware to determine if an object's bounding volume is visible or occluded by other objects. The hierarchical occlusion map approach divides the scene into a hierarchical structure, such as an octree or a binary space partitioning tree. The algorithm then performs occlusion tests at different levels of the hierarchy to determine occlusion relationships between objects. This approach can efficiently handle complex scenes with many occluders and occludees. Occlusion culling is particularly useful in scenes with complex geometry and large numbers of objects. By selectively rendering only the visible objects, we can achieve significant performance improvements and maintain real-time rendering rates. In conclusion, rendering techniques such as frustum culling and occlusion culling are essential for optimizing the rendering process in computer graphics. These techniques help reduce the computational workload by eliminating objects that are outside the view frustum or occluded by other objects. By efficiently culling invisible or occluded objects, we can improve rendering performance and achieve real-time rendering in complex scenes. 1.4 Optimization in computer graphics. Optimization plays a crucial role in computer graphics, as it allows for the efficient rendering of complex scenes in real-time applications. In this section, we will explore some of the key optimization techniques used in computer graphics, including frustum culling and occlusion culling. 1.4.1 Frustum culling. Frustum culling is a technique used to determine which objects in a scene are visible within the camera's view frustum. The view frustum is a truncated pyramid-shaped volume that represents the portion of the world that is visible to the camera. By eliminating objects that are outside the frustum, we can significantly reduce the number of objects that need to be rendered, resulting in improved performance. The frustum culling process involves a series of tests to determine if an object is completely outside, partially inside, or completely inside the frustum. The most common test is the bounding volume test, where each object is enclosed within a bounding volume, such as a sphere or an axis-aligned bounding box. If the bounding volume of an object is completely outside the frustum, it can be safely culled from the rendering process. There are various algorithms available for frustum culling, including the axis-aligned bounding box AABB test, oriented bounding box OBB test, and sphere test. Each algorithm has its own advantages and disadvantages, depending on the complexity of the scene and the shape of the objects. 1.4.2 Occlusion culling. Occlusion culling is another optimization technique used in computer graphics to determine which objects are occluded or hidden from view by other objects in the scene. By identifying occluded objects, we can avoid rendering them, resulting in significant performance improvements. The occlusion culling process involves determining the visibility of objects based on their relationship to other objects in the scene. This is typically done by creating an occlusion buffer or a visibility buffer, which stores information about the visibility of each pixel in the scene. By comparing the depth values of objects in the buffer, we can determine if an object is occluded by another object. There are several occlusion culling techniques available, including the depth buffer test, occlusion query, and hierarchical occlusion maps. The depth buffer test compares the depth values of objects during the rendering process to determine occlusion. Occlusion queries use hardware support to determine if an object is visible or occluded. Hierarchical occlusion maps divide the scene into smaller regions and store occlusion information for each region, allowing for efficient occlusion culling. 1.4.3 Benefits of optimization techniques. The optimization techniques discussed in this section provide several benefits in computer graphics applications. By reducing the number of objects that need to be rendered, frustum culling and occlusion culling significantly improve rendering performance. This is particularly important in real-time applications, such as video games and virtual reality, where maintaining a high frame rate is crucial for a smooth and immersive experience. Optimization techniques also help to conserve system resources, such as CPU and GPU processing power, memory, and bandwidth. By eliminating unnecessary rendering operations, these techniques allow for the efficient utilization of available resources, resulting in improved overall system performance. Furthermore, optimization techniques enable the rendering of more complex and detailed scenes by efficiently managing the rendering workload. By selectively rendering only the visible and unoccluded objects, developers can create visually stunning environments without sacrificing performance. 1.4.4 Considerations and limitations. While optimization techniques offer significant performance improvements, they also come with certain considerations and limitations. The effectiveness of frustum culling and occlusion culling depends on the complexity of the scene and the efficiency of the culling algorithms implemented. In scenes with a large number of objects or highly dynamic environments, the overhead of performing culling tests may outweigh the benefits gained. Therefore, it is essential to strike a balance between the complexity of the culling algorithms and the scene's complexity to achieve optimal performance. Additionally, optimization techniques may introduce artifacts or visual discrepancies if not implemented correctly. For example, objects may pop into view suddenly if they are not properly culled or occluded. Careful consideration and testing are required to ensure that the optimization techniques do not negatively impact the visual quality or user experience. In conclusion, optimization techniques such as frustum culling and occlusion culling are essential for achieving real-time rendering performance in computer graphics applications. By selectively rendering only the visible and unoccluded objects, these techniques improve rendering efficiency, conserve system resources, and enable the rendering of more complex scenes. However, developers must carefully consider the scene complexity and implement the techniques correctly to avoid artifacts and maintain visual quality. 2. Frustum culling. 2.1 What is frustum culling? Frustum culling is a technique used in computer graphics to optimize rendering by eliminating objects that are outside the view frustum. The view frustum is the portion of the 3D space that is visible on the screen. By removing objects that are not visible, frustum culling reduces the number of objects that need to be processed and rendered, resulting in improved performance. The view frustum is defined by 6 planes: near, far, left, right, top, and bottom. These planes form a pyramid-like shape with the camera at the apex. Any object that lies completely outside the view frustum is guaranteed to be invisible and can be safely discarded. Frustum culling works by performing a series of tests to determine if an object is inside or outside the view frustum. The most common test is the bounding volume test, where each object is enclosed in a bounding volume such as a sphere or an axis-aligned bounding box, AABB. If the bounding volume of an object is entirely outside any of the frustum planes, the object is culled. There are several algorithms used for frustum culling, each with its own advantages and limitations. One commonly used algorithm is the axis-aligned bounding box, AABB test. In this approach, the bounding box of an object is compared against the frustum planes. If any part of the bounding box lies outside the frustum, the object is culled. This test is relatively fast and simple to implement, making it a popular choice for real-time applications. Another algorithm is the sphere test, where the distance between the center of the bounding sphere and the frustum planes is compared to the radius of the sphere. If the distance is greater than the radius, the sphere is outside the frustum and the object is culled. This test is slightly more expensive than the AABB test but provides a tighter fit for objects with irregular shapes. In addition to these basic tests, more advanced techniques can be used to further optimize frustum culling. One such technique is hierarchical frustum culling, where the scene is divided into a hierarchy of bounding volumes. This allows for faster culling by quickly discarding entire groups of objects that are outside the frustum. Implementing frustum culling involves iterating through all the objects in the scene and performing the necessary tests to determine their visibility. This process can be performed on the CPU or the GPU, depending on the specific requirements of the application. On the CPU, frustum culling can be done using traditional programming techniques, while on the GPU, it can be implemented using shaders and specialized algorithms. When implementing frustum culling, it is important to consider performance considerations. While frustum culling can significantly improve rendering performance by reducing the number of objects to be processed, it also introduces additional overhead. The cost of performing the culling tests and managing the data structures for storing the objects can impact the overall performance. Therefore, it is crucial to strike a balance between the benefits of culling and the cost of the culling process itself. In conclusion, frustum culling is a vital technique in computer graphics that helps optimize rendering performance by eliminating objects that are outside the view frustum. By discarding invisible objects, frustum culling reduces the workload on the rendering pipeline, resulting in faster and more efficient rendering. Various algorithms and optimizations can be employed to implement frustum culling, and careful consideration must be given to the performance trade-offs involved. 2.2 Frustum culling algorithms. Frustum culling is a fundamental technique used in computer graphics to optimize rendering by eliminating objects that are outside the view frustum. The view frustum is the portion of the world that is visible to the camera or the viewer. By removing objects that are not visible, frustum culling reduces the number of objects that need to be processed, resulting in significant performance improvements. Frustum culling algorithms determine whether an object is inside or outside the view frustum by performing geometric tests. There are several commonly used frustum culling algorithms, each with its own advantages and limitations. In this section, we will explore some of these algorithms and discuss their characteristics. 2.2.1 Axis-aligned bounding box, AABB test. One of the simplest and most widely used frustum culling algorithms is the axis-aligned bounding box, AABB test. In this algorithm, each object in the scene is enclosed within an axis-aligned bounding box, which is a rectangular box aligned with the coordinate axes. The AABB test checks whether the bounding box of an object intersects with or is completely outside the view frustum. If the bounding box is outside the frustum, the object is culled and not rendered. The AABB test is efficient and easy to implement, making it a popular choice for frustum culling. However, it can be overly conservative in some cases, resulting in objects that are partially visible being culled. To address this issue, more advanced algorithms have been developed. 2.2.2 View frustum plane test. The view frustum plane test is a more accurate frustum culling algorithm that takes into account the shape of the view frustum. Instead of using a simple bounding box, this algorithm checks whether each vertex of an object is on the correct side of each frustum plane. If all vertices are on the correct side of all planes, the object is considered to be inside the frustum and is rendered, otherwise, it is culled. The view frustum plane test provides better accuracy than the AABB test and can handle more complex frustum shapes. However, it requires additional computations for each vertex, which can impact performance, especially for scenes with a large number of objects. 2.2.3 Hierarchical view frustum culling. Hierarchical view frustum culling is an optimization technique that reduces the number of frustum culling tests by organizing objects into a hierarchical structure. This structure, often implemented as an octree or a bounding volume hierarchy, divides the scene into smaller regions or nodes. Each node represents a portion of the scene and contains a list of objects that are potentially visible within that region. During the frustum culling process, the hierarchical structure is traversed, and only the nodes that intersect with the view frustum are further tested. This approach eliminates the need to test individual objects that are contained within culled nodes, resulting in significant performance improvements. Hierarchical view frustum culling is particularly effective in scenes with a high level of object occlusion, where many objects are hidden behind others. By quickly eliminating entire regions of the scene, This algorithm reduces the number of objects that need to be considered for rendering, leading to substantial performance gains. 2.2.4 Occlusion culling integration. Frustum culling can be further enhanced by integrating it with occlusion culling techniques. Occlusion culling determines whether an object is visible or hidden based on its occlusion by other objects in the scene. By combining frustum culling with occlusion culling, objects that are outside the view frustum and occluded by other objects can be efficiently culled, resulting in even greater performance improvements. The integration of frustum culling and occlusion culling requires additional computations to determine occlusion relationships between objects. However, the benefits of reducing the number of objects to be rendered outweigh the computational overhead, especially in complex scenes with a high level of occlusion. In conclusion, frustum culling algorithms play a crucial role in optimizing computer graphics rendering by eliminating objects that are outside the view frustum. The choice of algorithm depends on the specific requirements of the application, balancing accuracy and performance. By efficiently culling objects that are not visible, frustum culling significantly improves rendering performance, allowing for more complex and realistic graphics in real-time applications. 2.3 Implementation of frustum culling. Frustum culling is a technique used in computer graphics to optimize rendering by eliminating objects that are outside the view frustum. The view frustum is the portion of the 3D space that is visible on the screen. By removing objects that are not visible, frustum culling reduces the number of objects that need to be processed, resulting in improved performance. 2.3.1 Overview of frustum culling. The implementation of frustum culling involves several steps. First, we need to define the view frustum. The view frustum is defined by 6 planes: near, far, left, right, top, and bottom. These planes form a pyramid-like shape that represents the visible portion of the scene. To determine whether an object is inside or outside the frustum, we perform a simple test using the object's bounding volume. The bounding volume is a simplified shape that encapsulates the object, such as a sphere or an axis-aligned bounding box. If the bounding volume is completely outside any of the frustum planes, we can safely discard the object. 2.3.2 Frustum culling algorithms. There are several algorithms available for frustum culling, each with its own advantages and limitations. One commonly used algorithm is the bounding sphere test. In this algorithm, we calculate the distance between the center of the bounding sphere and each frustum plane. If the distance is greater than the radius of the sphere, the object is outside the frustum. Another popular algorithm is the axis-aligned bounding box (AABB) test. In this algorithm, we check if any of the 8 corners of the AABB are outside any of the frustum planes. If all corners are inside the frustum, the object is considered visible. Other algorithms, such as the oriented bounding box (OBB) test and the convex hull test, can be used for more complex objects. These algorithms involve more calculations but can provide more accurate results. 2.3.3 Implementation steps. To implement frustum culling, we need to follow a series of steps. Define the view frustum by calculating the 6 frustum planes based on the camera's position and orientation. For each object in the scene, calculate its bounding volume, e.g., bounding sphere, AABB, OBB. Perform the frustum culling test for each object by checking if the bounding volume is outside any of the frustum planes. If the object is outside the frustum, discard it from the rendering process. If the object is inside the frustum, continue with the rendering process. 2.3.4 Optimizations and considerations. While frustum culling can significantly improve rendering performance, there are some optimizations and considerations to keep in mind. Spatial partitioning. Divide the scene into smaller regions or cells to reduce the number of objects that need to be tested against the frustum. Techniques such as octrees or quadtrees can be used for efficient spatial partitioning. Level of detail (LOD). Use different levels of detail for objects based on their distance from the camera. Objects that are far away can be rendered with lower detail or even replaced with simpler representations. Dynamic frustum culling. Update the frustum culling calculations dynamically as the camera moves or rotates. This ensures that objects that were previously outside the frustum but are now visible are included in the rendering process. Hierarchical frustum culling. Use a hierarchical approach to frustum culling by dividing the scene into a hierarchy of bounding volumes. This allows for faster culling by quickly discarding entire groups of objects that are outside the frustum. Object culling order. Consider the order in which objects are tested for frustum culling. Sorting objects based on their distance from the camera can improve cache coherency and reduce the number of unnecessary calculations. By implementing frustum culling effectively and considering these optimizations, developers can achieve significant performance improvements in their computer graphics applications. This technique is particularly useful in scenes with a large number of objects or complex environments where rendering efficiency is crucial. 2.4 Performance considerations. When implementing frustum culling and occlusion culling techniques in computer graphics, it is essential to consider their impact on performance. These optimization techniques are designed to reduce the number of objects that need to be rendered, thus improving the overall efficiency of the rendering process. However, improper implementation or misuse of these techniques can lead to unintended consequences and potential performance bottlenecks. In this section, we will explore some important performance considerations when using frustum culling and occlusion culling. 2.4.1 Frustum culling performance. Frustum culling is a technique used to determine whether an object is within the view frustum of the camera. By discarding objects that are outside the frustum, unnecessary computations and rendering operations can be avoided. However, the performance of frustum culling depends on several factors. 2.4.1.1 Frustum calculation. The accuracy and efficiency of frustum culling heavily rely on the accuracy of the frustum calculation. The frustum needs to be updated whenever the camera moves or changes its orientation. If the frustum calculation is not performed correctly or is too frequent, it can introduce unnecessary overhead and impact performance. Therefore, it is crucial to optimize the frustum calculation algorithm to ensure it is both accurate and efficient. 2.4.1.2 Object bounding volume. Frustum culling relies on the use of bounding volumes, such as bounding spheres or bounding boxes, to quickly determine if an object is within the frustum. The choice of bounding volume can significantly impact the performance of frustum culling. Bounding spheres are generally faster to compute and test against, but they may not provide the tightest fit for complex objects. On the other hand, bounding boxes can provide a tighter fit but require more computational resources. It is important to strike a balance between accuracy and performance when choosing the appropriate bounding volume for frustum culling. 2.4.1.3 Object distribution. The distribution of objects in the scene can also affect the performance of frustum culling. If the scene contains a large number of objects that are mostly outside the frustum, the benefits of frustum culling will be more pronounced. However, if the majority of objects are within the frustum, the performance gains may be minimal. It is important to consider the object distribution when deciding whether to apply frustum culling and to evaluate its impact on performance. 2.4.2 Occlusion culling performance. Occlusion culling is a technique used to determine whether an object is occluded by other objects in the scene and can be safely skipped from rendering. Like frustum culling, occlusion culling can significantly improve rendering performance by reducing the number of objects that need to be processed. However, there are several performance considerations to keep in mind when implementing occlusion culling. 2.4.2.1 Occlusion query. Occlusion culling often involves the use of occlusion queries, which are GPU operations that determine if a particular object or group of objects is visible. These queries can introduce additional overhead and impact performance. It is important to carefully manage and optimize the occlusion query process to minimize its impact on rendering performance. This can include batching occlusion queries, using hierarchical occlusion culling, or employing other techniques to reduce the number of queries performed. 2.4.2.2 Object complexity. The complexity of objects in the scene can also affect the performance of occlusion culling. Highly detailed or complex objects may require more computational resources to perform occlusion queries accurately. Additionally, objects with transparent or semi-transparent materials can pose challenges for occlusion culling, as their visibility may depend on the order in which objects are rendered. It is important to consider the complexity of objects in the scene and evaluate the trade-off between accuracy and performance when implementing occlusion culling. 2.4.2.3 Dynamic objects. Occlusion culling is particularly effective for static or semi-static objects in the scene. However, the presence of dynamic objects can introduce additional challenges. Dynamic objects may change their visibility state frequently, requiring more frequent occlusion queries and potentially impacting performance. It is important to carefully manage the occlusion culling process for dynamic objects to ensure that the benefits outweigh the additional computational overhead. 2.4.3 Balancing optimization and overhead. When implementing frustum culling and occlusion culling, it is crucial to strike a balance between optimization and overhead. While these techniques can significantly improve rendering performance, they also introduce additional computational and memory overhead. It is important to carefully evaluate the benefits and drawbacks of these techniques in the context of the specific application and hardware platform. Furthermore, it is worth noting that the effectiveness of frustum culling and occlusion culling can vary depending on the scene complexity, object distribution, and camera movement. It is recommended to profile and benchmark the performance of these techniques in different scenarios to ensure optimal performance. In conclusion, frustum culling and occlusion culling are powerful optimization techniques in computer graphics that can greatly improve rendering performance. However, their implementation requires careful consideration of factors such as frustum calculation, object bounding volumes, object distribution, occlusion query management, object complexity, and dynamic objects. By understanding and addressing these performance considerations, developers can harness the full potential of frustum culling and occlusion culling to achieve efficient and visually appealing graphics applications. 3. Occlusion culling. 3.1 What is occlusion culling? In computer graphics, occlusion culling is a technique used to optimize the rendering process by selectively rendering only the objects that are visible to the camera. It is based on the concept of occlusion, which refers to the blocking or hiding of one object by another in a 3D scene. By identifying and excluding the occluded objects from the rendering process, occlusion culling significantly reduces the computational workload and improves the overall performance of the graphics system. 3.1.1 Occlusion culling techniques. There are several techniques used in occlusion culling, each with its own advantages and limitations. Here are some commonly used techniques. 1. View frustum culling. View frustum culling is a technique that involves checking whether an object lies within the view frustum of the camera. The view frustum is the portion of the 3D space that is visible to the camera and is defined by 6 planes: near, far, left, right, top, and bottom. By performing simple geometric tests, objects outside the view frustum can be quickly discarded, as they are not visible to the camera. 2. Occlusion queries. Occlusion queries involve using the graphics hardware to determine whether an object is occluded by other objects in the scene. This technique works by rendering the potentially occluding objects into a separate buffer, known as the occlusion buffer. The occlusion buffer stores information about the number of pixels that pass the depth test. By querying the occlusion buffer, objects that are completely occluded can be skipped during the rendering process. 3. Portal culling. Portal culling is a technique commonly used in indoor environments, where rooms are connected by portals or doorways. It involves dividing the scene into different rooms and determining which rooms are visible from the current room. By only rendering the visible rooms and their contents, portal culling can greatly reduce the number of objects that need to be rendered. 4. Hierarchical occlusion maps. Hierarchical occlusion maps divide the scene into a hierarchy of cells or tiles. Each cell contains a small image, known as an occlusion map, which represents the visibility of objects within that cell. By traversing the hierarchy and testing the occlusion maps, objects that are occluded by other objects can be quickly identified and culled. 3.1.2 Implementation of occlusion culling. The implementation of occlusion culling involves several steps. 1. Scene partitioning. The first step is to partition the scene into smaller regions or cells. This can be done using techniques such as spatial partitioning, where the scene is divided into a hierarchy of bounding volumes or grids. Each cell represents a portion of the scene that can be independently culled. 2. Occlusion testing. Once the scene is partitioned, occlusion testing is performed for each cell. This involves determining which objects within the cell are potentially occluded by other objects. Techniques such as view frustum culling, occlusion queries, or hierarchical occlusion maps can be used to perform the occlusion testing. 3. Visibility determination. After the occlusion testing, the visibility of each object is determined. Objects that are completely occluded can be culled, while objects that are partially visible or not occluded are marked as visible. 4. Rendering. Finally, the visible objects are rendered using traditional rendering techniques. The rendering process only considers the objects that have been marked as visible, resulting in improved performance and reduced computational workload. 3.1.3 Performance considerations. While occlusion culling can greatly improve the performance of a graphics system, there are some considerations to keep in mind. 1. Overhead. The implementation of occlusion culling introduces additional overhead in terms of memory usage and computational complexity. The partitioning of the scene, occlusion testing, and visibility determination all require additional resources and processing time. It is important to strike a balance between the performance gains achieved through occlusion culling and the overhead introduced by its implementation. 2. Dynamic scenes. Occlusion culling techniques are most effective in static or semi-static scenes where the occlusion relationships between objects do not change frequently. In dynamic scenes where objects move or change their visibility, the occlusion culling process needs to be updated continuously to reflect the changes. This can introduce additional computational overhead and may require more sophisticated techniques to handle dynamic occlusion. 3. Occlusion accuracy. The accuracy of occlusion culling techniques can have a significant impact on the visual quality of the rendered scene. In some cases, objects that are partially occluded may still contribute to the overall scene composition. Balancing the accuracy of occlusion culling with the performance gains is crucial to ensure a visually pleasing result. In conclusion, occlusion culling is a powerful technique in computer graphics that optimizes the rendering process by selectively rendering only the visible objects. By utilizing techniques such as view frustum culling, occlusion queries, portal culling, and hierarchical occlusion maps, occlusion culling significantly reduces the computational workload and improves the performance of graphics systems. However, careful consideration must be given to the implementation and performance trade-offs to achieve the desired balance between performance and visual quality. 3.2 Occlusion culling techniques. Occlusion culling is a fundamental optimization technique in computer graphics that aims to reduce the amount of unnecessary rendering by identifying and eliminating objects that are not visible to the camera. By selectively rendering only the objects that are visible, occlusion culling significantly improves the performance and efficiency of rendering algorithms. 3.2.1 View frustum culling. One of the most commonly used techniques in occlusion culling is view frustum culling. The view frustum is a geometric shape that represents the portion of the 3D scene that is visible to the camera. It is defined by 6 planes: near, far, left, right, top, and bottom. Any object or part of an object that falls outside of the view frustum is considered occluded and can be safely culled. To perform view frustum culling, each object in the scene is tested against the 6 planes of the frustum. If an object is entirely outside any of the planes, it is completely occluded and can be safely discarded from the rendering process. On the other hand, if an object intersects or is contained within the frustum, it is considered potentially visible and needs to be further evaluated. 3.2.2 Occlusion queries. Occlusion queries are another technique used in occlusion culling. They involve querying the graphics hardware to determine whether a particular object or group of objects is visible or occluded. This is achieved by rendering the objects into a special buffer called an occlusion query buffer, which keeps track of the number of pixels that pass the depth test. The occlusion query process works as follows. First, the occlusion query buffer is cleared. Then, the objects of interest are rendered with a special occlusion query shader. The shader counts the number of pixels that pass the depth test and writes the result to the occlusion query buffer. Finally, the result is read back from the buffer and used to determine whether the objects are visible or occluded. By using occlusion queries, objects that are completely occluded can be quickly identified and culled, saving valuable rendering resources. However, it is important to note that occlusion queries introduce some overhead due to the additional rendering and buffer operations involved. 3.2.3 Hierarchical occlusion culling. Hierarchical occlusion culling is a technique that leverages spatial partitioning structures, such as octrees or bounding volume hierarchies, to accelerate the occlusion culling process. Instead of testing each object individually against the view frustum or occlusion queries, hierarchical occlusion culling groups objects into larger spatial regions and performs visibility tests on these regions. The idea behind hierarchical occlusion culling is to exploit the spatial coherence of the scene. Objects that are close to each other are more likely to be occluded or visible together. By organizing objects into spatial hierarchies, the visibility of entire regions can be determined based on the visibility of their parent nodes. This reduces the number of individual visibility tests and improves the overall efficiency of occlusion culling. 3.2.4 Portal-based occlusion culling. Portal-based occlusion culling is a technique commonly used in indoor or enclosed environments. It involves dividing the scene into interconnected rooms or areas and placing portals between them. A portal is a geometric shape that represents a doorway or opening between two areas. During the occlusion culling process, visibility tests are performed between portals to determine which areas are visible from each other. If an area is not visible through any portal, it can be safely culled from the rendering process. This technique exploits the fact that objects in different areas are usually occluded from each other and eliminates the need to perform visibility tests between every object in the scene. Portal-based occlusion culling can significantly reduce the number of objects that need to be rendered, especially in complex indoor environments with many interconnected rooms. However, it requires careful placement and management of portals to ensure accurate occlusion culling results. 3.2.5 Imposter-based occlusion culling. Imposter-based occlusion culling is a technique that replaces complex or distant objects with simplified representations called imposters. An imposter is a 2D image or a simplified 3D model that approximates the appearance of the original object from the camera's viewpoint. During the occlusion culling process, objects that are deemed occluded or too far away are replaced with their corresponding imposters. These imposters are then rendered instead of the original objects, reducing the computational cost of rendering complex geometry. When the imposters become visible again, they are replaced with the original objects. Imposter-based occlusion culling is particularly useful for large-scale environments or objects with high geometric complexity. By using imposters, the rendering workload can be significantly reduced without sacrificing visual quality. However, imposter generation and management can introduce additional overhead and require careful consideration to ensure seamless transitions between imposters and original objects. In conclusion, occlusion culling techniques play a crucial role in optimizing computer graphics rendering by selectively rendering only the visible objects. View frustum culling, occlusion queries, hierarchical occlusion culling, portal-based occlusion culling, and imposter-based occlusion culling are some of the commonly used techniques that improve rendering performance and efficiency. Each technique has its strengths and limitations, and their appropriate usage depends on the specific requirements of the application or scene. 3.3 Implementation of occlusion culling. Occlusion culling is a technique used in computer graphics to optimize rendering by reducing the number of objects that need to be rendered. It works by determining which objects are not visible to the camera and therefore can be culled from the rendering process. This helps to improve performance by reducing the amount of unnecessary rendering calculations. 3.3.1 Occlusion culling algorithms. There are several algorithms that can be used to implement occlusion culling. One commonly used algorithm is the occlusion query technique. This technique involves querying the graphics hardware to determine if a particular object is visible or occluded by other objects in the scene. The occlusion query technique works by rendering the potentially occluded objects into a separate buffer, known as the occlusion query buffer. This buffer is then used to perform queries on the graphics hardware to determine if the objects are visible or occluded. If an object is occluded, it can be culled from the rendering process, saving valuable rendering resources. Another algorithm used for occlusion culling is the hierarchical occlusion map (HOME) technique. This technique involves dividing the scene into a hierarchy of cells, where each cell represents a portion of the scene. The visibility of each cell is determined by rendering it into a separate buffer and performing occlusion queries on the graphics hardware. The results of these queries are then used to determine the visibility of the cells at higher levels of the hierarchy. This allows for efficient culling of large portions of the scene that are not visible to the camera. 3.3.2 Occlusion culling techniques. There are several techniques that can be used in conjunction with occlusion culling to further optimize the rendering process. One such technique is view frustum culling. View frustum culling involves culling objects that are outside the view frustum of the camera. The view frustum is a geometric shape that represents the portion of the scene that is visible to the camera. By culling objects that are outside the view frustum, unnecessary rendering calculations can be avoided. Another technique that can be used with occlusion culling is level of detail LOD culling. LOD culling involves using different levels of detail for objects depending on their distance from the camera. Objects that are far away from the camera can be rendered with lower levels of detail, reducing the number of polygons that need to be rendered. This can significantly improve performance, especially in scenes with large numbers of objects. 3.3.3 Implementation Considerations. When implementing occlusion culling, there are several considerations that need to be taken into account. One important consideration is the trade-off between the cost of performing occlusion queries and the potential performance gains. Performing occlusion queries can be computationally expensive, especially for complex scenes with large numbers of objects. Therefore, it is important to carefully balance the number of occlusion queries performed with the potential performance gains achieved. Another consideration is the accuracy of the occlusion culling technique. While occlusion culling can significantly improve performance, it is important to ensure that objects are not incorrectly culled from the rendering process. This can result in objects disappearing or flickering in the rendered scene. Therefore, it is important to carefully test and optimize the occlusion culling implementation to ensure accurate and reliable results. Additionally, the efficiency of the occlusion culling implementation can be influenced by the organization and structure of the scene data. Using spatial partitioning techniques, such as bounding volume hierarchies or octrees, can help to optimize the occlusion culling process by reducing the number of objects that need to be tested for occlusion. In conclusion, occlusion culling is an important technique in computer graphics for optimizing rendering performance. By determining which objects are not visible to the camera and culling them from the rendering process, unnecessary rendering calculations can be avoided. Implementing occlusion culling involves using algorithms such as occlusion queries or hierarchical occlusion maps, and can be further optimized by using techniques like view frustum culling and level of detail culling. However, careful consideration must be given to the trade-offs, accuracy, and efficiency of the implementation to ensure optimal performance and visual quality. 3.4 Performance Considerations. When implementing frustum culling and occlusion culling techniques in computer graphics, it is essential to consider their impact on performance. These optimization techniques can significantly improve the rendering efficiency by reducing the number of objects that need to be processed and rendered. However, improper implementation or misuse of these techniques can lead to performance bottlenecks or visual artifacts. In this section, we will discuss some important performance considerations related to frustum culling and occlusion culling. 3.4.1 Frustum culling performance considerations. Frustum culling is a technique used to determine which objects in a scene are visible within the camera's view frustum. While it can greatly reduce the number of objects that need to be processed and rendered, it also introduces some performance considerations that need to be taken into account. View frustum calculation. One of the key factors affecting the performance of frustum culling is the calculation of the view frustum. The view frustum represents the portion of the world that is visible to the camera. It is typically defined by 6 planes: near, far, left, right, top, and bottom. The calculation of these planes can be computationally expensive, especially if the camera's projection matrix needs to be updated frequently. To optimize this process, it is common to calculate the view frustum only when necessary, such as when the camera moves or changes its field of view. Object bounds calculation. Frustum culling relies on the bounding volumes of objects to determine their visibility. The calculation of these bounding volumes can also impact performance. If the bounding volumes are too simple or inaccurate, objects that should be culled might still be considered visible, leading to unnecessary processing and rendering. On the other hand, if the bounding volumes are too complex or detailed, the calculation itself can become a performance bottleneck. Striking the right balance between accuracy and efficiency is crucial. Spatial data structures. Efficient spatial data structures play a vital role in frustum culling performance. These data structures, such as octrees or bounding volume hierarchies, organize the objects in the scene spatially, allowing for faster culling decisions. However, the construction and maintenance of these data structures can introduce additional overhead. It is important to consider the trade-off between the time spent building and updating the data structure versus the time saved during frustum culling. 3.4.2 Occlusion culling performance considerations. Occlusion culling is a technique used to determine which objects in a scene are occluded or hidden from view by other objects. Like frustum culling, occlusion culling can significantly improve rendering performance by reducing the number of objects that need to be processed and rendered. However, it also comes with its own set of performance considerations. Occlusion query overhead. One of the primary performance considerations in occlusion culling is the overhead introduced by occlusion queries. Occlusion queries are used to determine if an object is visible or occluded. However, issuing and resolving occlusion queries can be a costly operation, especially if there are a large number of objects in the scene. It is crucial to carefully manage the number and placement of occlusion queries to minimize the impact on performance. Occluder complexity. The complexity of occluders, the objects that block the view of other objects, can also impact occlusion culling performance. If the occluders are too complex or detailed, the occlusion culling algorithm may spend a significant amount of time processing and testing occlusion for each object. Simplifying the occluders or using more efficient occlusion culling techniques, such as hierarchical occlusion maps, can help mitigate this performance impact. Dynamic environments. Occlusion culling becomes more challenging in dynamic environments where objects can move or change their visibility status frequently. Updating the occlusion culling data structures or occlusion queries in real time can introduce additional overhead. It is important to carefully balance the need for accurate occlusion culling with the performance impact of updating the occlusion data structures. Conclusion. Frustum culling and occlusion culling are powerful techniques for optimizing the rendering process in computer graphics. However, their implementation requires careful consideration of various performance factors. By properly managing view frustum calculations, object bounds, spatial data structures, occlusion query overhead, occluder complexity, and dynamic environments, developers can achieve efficient and visually appealing rendering performance. It is crucial to strike the right balance between accuracy and efficiency to ensure a smooth and immersive graphics experience. 4. Level of Detail (LOD). 4.1 Introduction to Level of Detail. In computer graphics, level of detail (LOD) is a technique used to optimize the rendering process by dynamically adjusting the level of detail of objects based on their distance from the viewer. The goal of LOD is to maintain a balance between visual quality and computational efficiency, ensuring that objects appear detailed when they are close to the viewer and less detailed when they are far away. 4.1.1 What is level of detail? Level of detail refers to the process of representing objects in different levels of complexity based on their distance from the viewer. As objects move further away, they become smaller on the screen, and the level of detail required to render them accurately decreases. By reducing the complexity of objects in the distance, LOD techniques can significantly improve the performance of real-time rendering systems. The concept of LOD is based on the principle that the human visual system is more sensitive to details when objects are closer and less sensitive when objects are farther away. By taking advantage of this perceptual characteristic, LOD techniques can reduce the number of polygons, textures, and other resources required to render a scene, resulting in faster rendering times and improved frame rates. 4.1.2 LOD Techniques. There are several LOD techniques that can be employed to optimize the rendering process. 4.1.2.1 Geometry LOD. Geometry LOD involves reducing the complexity of an object's geometry based on its distance from the viewer. This can be achieved by using simplified versions of the object's mesh or by dynamically adjusting the level of detail of the mesh. For example, a high-resolution mesh can be replaced with a lower-resolution mesh as the object moves further away, reducing the number of polygons that need to be rendered. 4.1.2.2 Texture LOD. Texture LOD involves using lower-resolution textures for objects that are far away from the viewer. This can be achieved by dynamically swapping textures based on the distance of the object. By using lower-resolution textures, the amount of memory required for texture storage is reduced, resulting in improved performance. 4.1.2.3 Shader LOD. Shader LOD involves using simpler shaders for objects that are far away from the viewer. This can be achieved by reducing the number of calculations performed in the shader or by using pre-computed lighting information. By using simpler shaders, the computational load on the graphics processing unit, GPU, is reduced, resulting in improved performance. 4.1.3 Implementation of LOD. The implementation of LOD involves several steps. 4.1.3.1 Distance calculation. The first step in implementing LOD is to calculate the distance between the viewer and each object in the scene. This can be done using various distance calculation techniques, such as Euclidean distance or Manhattan distance. The distance calculation is typically performed in the vertex shader or in a separate stage of the rendering pipeline. 4.1.3.2 Level of detail selection. Once the distance between the viewer and each object is calculated, the next step is to determine the appropriate level of detail for each object. This can be done using a LOD selection algorithm, which takes into account factors such as the distance, size, and importance of the object. The LOD selection algorithm can be implemented in the CPU or GPU, depending on the specific requirements of the application. 4.1.3.3 Geometry, Texture, and Shader Switching. After the level of detail for each object is determined, the next step is to switch the geometry, texture, and shader based on the selected level of detail. This can be done by swapping the object's mesh, texture, and shader with the appropriate version for the selected level of detail. The switching can be performed in the CPU or GPU, depending on the specific implementation. 4.1.4 Performance Considerations. While LOD techniques can significantly improve the performance of real-time rendering systems, there are some considerations to keep in mind. 4.1.4.1 Artifacts. One of the challenges of LOD is the potential for visual artifacts, such as popping or morphing, when switching between different levels of detail. These artifacts can be minimized by using smooth transitions between levels of detail or by applying techniques such as morphing or blending. 4.1.4.2 Memory Usage. LOD techniques can reduce the memory usage of a rendering system by using lower resolution textures and simplified geometry. However, it is important to carefully manage the memory usage to avoid excessive memory consumption or texture thrashing. This can be achieved by using efficient memory management techniques, such as texture streaming or dynamic texture loading. 4.1.4.3 Performance Impact. While LOD techniques can improve the performance of a rendering system, they can also introduce additional computational overhead. The distance calculation, level of detail selection, and geometry, texture, and shader switching all require additional processing, which can impact the overall performance of the system. It is important to carefully balance the performance gains with the additional computational cost. In conclusion, level of detail (LOD) is a powerful technique for optimizing the rendering process in computer graphics. By dynamically adjusting the level of detail of objects based on their distance from the viewer, LOD techniques can significantly improve the performance of real-time rendering systems. However, careful consideration must be given to factors such as visual artifacts, memory usage, and performance impact to ensure a successful implementation of LOD. 4.2 LOD Techniques. Level of detail (LOD) is a technique used in computer graphics to optimize the rendering process by dynamically adjusting the level of detail of objects based on their distance from the viewer. LOD techniques are essential for improving performance and reducing computational requirements in real-time rendering applications. In this section, we will explore various LOD techniques and their implementation in computer graphics. 4.2.1 LOD Basics. Before diving into the specific LOD techniques, let's first understand the basic concept behind LOD. The idea behind LOD is to render objects with varying levels of detail based on their distance from the viewer. Objects that are far away from the viewer can be rendered with lower detail, while objects that are closer require higher detail to maintain visual fidelity. The primary goal of LOD is to balance visual quality and performance. By reducing the level of detail for distant objects, we can save computational resources and improve rendering performance. On the other hand, maintaining high detail for nearby objects ensures a visually pleasing experience for the viewer. 4.2.2 LOD Techniques. There are several LOD techniques commonly used in computer graphics. Let's explore some of the most popular ones. 4.2.2.1 Geometry LOD. Geometry LOD involves dynamically adjusting the complexity of an object's geometry based on its distance from the viewer. This technique is commonly used for complex 3D models, such as characters or architectural structures. As an object moves further away, the number of polygons used to represent it is reduced, resulting in a simplified version of the object. This reduction in geometry complexity significantly improves rendering performance without sacrificing visual quality. Implementing geometry LOD requires creating multiple versions of an object with varying levels of detail. These versions are typically pre-computed and stored in a LOD hierarchy. As the object moves closer or farther from the viewer, the appropriate LOD level is selected and rendered. 4.2.2.2 Texture LOD. Texture LOD involves dynamically adjusting the resolution of textures applied to objects based on their distance from the viewer. Textures with higher resolution require more memory and processing power to render. By reducing the texture resolution for distant objects, we can save computational resources without significantly impacting visual quality. Texture LOD can be implemented by creating multiple versions of a texture with varying resolutions. These versions are stored in a texture LOD hierarchy, similar to geometry LOD. As an object moves closer or farther from the viewer, the appropriate texture LOD level is selected and applied to the object. 4.2.2.3 Shader LOD. Shader LOD involves dynamically adjusting the complexity of shaders applied to objects based on their distance from the viewer. Shaders are responsible for calculating the color and lighting effects on objects. By reducing the complexity of shaders for distant objects, we can improve rendering performance. Shader LOD can be implemented by creating multiple versions of shaders with varying complexity. These versions are stored in a shader LOD hierarchy. As an object moves closer or farther from the viewer, the appropriate shader LOD level is selected and applied to the object. 4.2.2.4 Level of detail for terrain. Terrain rendering often requires special LOD techniques due to the large-scale nature of the environment. One common technique is to use a hierarchical representation of the terrain, such as a quadtree or an octree. The terrain is divided into smaller patches, and the level of detail is adjusted based on the viewer's position and distance. As the viewer moves closer to a patch, higher resolution geometry and textures are used to render the terrain. Conversely, as the viewer moves away, lower resolution representations are used. This dynamic adjustment of the terrain's level of detail ensures efficient rendering of large-scale environments. 4.2.3 LOD Implementation. Implementing LOD techniques requires careful consideration of the rendering pipeline and the underlying data structures. LOD hierarchies need to be constructed and managed efficiently to ensure smooth transitions between different levels of detail. For geometry LOD, the LOD hierarchy can be constructed using techniques like mesh simplification or level of detail algorithms such as the quadratic error metric (QEM). These algorithms analyze the geometry of an object and generate simplified versions with reduced polygon count. Texture LOD can be implemented by generating multiple versions of textures with varying resolutions. These textures can be stored in a texture atlas or managed using texture streaming techniques to ensure efficient memory usage. Shader LOD can be achieved by creating multiple versions of shaders with varying complexity. These shaders can be managed using shader permutation techniques, where different shader variants are compiled and selected at runtime based on the desired level of detail. For terrain LOD, hierarchical data structures like quadtree or octree can be used to manage the level of detail. These data structures divide the terrain into smaller patches, and the appropriate level of detail is selected based on the viewer's position. 4.2.4 Performance considerations. While LOD techniques can significantly improve rendering performance, there are some performance considerations to keep in mind. LOD transitions. Smooth transitions between different levels of detail are crucial to avoid visual artifacts. Careful management of LOD transitions is necessary to ensure a seamless viewing experience. Memory usage. LOD hierarchies and multiple versions of geometry, textures, and shaders require additional memory. Efficient memory management techniques, such as texture atlases and streaming, should be employed to minimize memory usage. CPU and GPU overhead. The computation required to manage LOD hierarchies and select appropriate levels of detail can introduce additional CPU overhead. Similarly, switching between different levels of detail can impact GPU performance. These overheads should be carefully balanced to achieve optimal performance. Artistic considerations. LOD techniques may impact the artistic intent of a scene. Artists and designers should be involved in the LOD implementation process to ensure that the visual quality of the rendered objects is maintained across different levels of detail. In conclusion, LOD techniques play a vital role in optimizing computer graphics rendering by dynamically adjusting the level of detail based on the viewer's distance. Geometry LOD, texture LOD, shader LOD, and terrain LOD are some of the commonly used techniques. Implementing LOD requires constructing efficient LOD hierarchies and managing transitions between different levels of detail. Performance considerations, such as LOD transitions, memory usage, CPU and GPU overhead, and artistic considerations, should be taken into account to achieve optimal results. 4.3 Implementation of LOD. Level of detail LOD is a technique used in computer graphics to optimize the rendering of complex scenes by dynamically adjusting the level of detail based on the distance between the camera and the objects in the scene. By reducing the level of detail for objects that are far away or not in the camera's view frustum, LOD can significantly improve rendering performance without sacrificing visual quality. 4.3.1 LOD techniques. There are several LOD techniques that can be implemented to achieve efficient rendering in computer graphics. These techniques involve simplifying the geometry or texture of objects based on their distance from the camera. Here are some commonly used LOD techniques. 4.3.1.1 Geometry LOD. Geometry LOD involves reducing the complexity of an object's geometry based on its distance from the camera. This can be achieved by using lower polygon models or by dynamically adjusting the level of detail of the object's mesh. For example, a high polygon model can be replaced with a simplified version when it is far away from the camera. This reduces the number of vertices and triangles that need to be processed, resulting in improved performance. 4.3.1.2 Texture LOD. Texture LOD involves using lower resolution textures for objects that are far away from the camera. This technique reduces the memory bandwidth required for texture fetching and improves rendering performance. The level of detail of the textures can be dynamically adjusted based on the distance of the object from the camera. This ensures that objects closer to the camera have higher resolution textures, while objects in the distance have lower resolution textures. 4.3.1.3 Imposters. Imposters are 2D representations of 3D objects that are used to approximate the appearance of distant objects. Instead of rendering the full 3D geometry of an object, imposters are rendered as billboards or sprites that always face the camera. These imposters can be pre-rendered from different viewpoints and stored as textures. When an object is far away, the imposter texture is used instead of rendering the full 3D geometry, resulting in significant performance improvements. 4.3.2 Implementation of LOD. Implementing LOD involves several steps, including determining the appropriate level of detail for each object, managing the transition between different levels of detail, and updating the LOD based on the camera's position and orientation. Here is an overview of the implementation process. 4.3.2.1 Level of detail selection. The first step in implementing LOD is to determine the appropriate level of detail for each object in the scene. This can be based on factors such as the distance from the camera, the size of the object on the screen, or a combination of both. The level of detail can be represented as a discrete value or as a continuous parameter that controls the complexity of the object's geometry or texture. 4.3.2.2 LOD transition. When transitioning between different levels of detail, it is important to ensure a smooth and seamless visual experience. Sudden changes in the level of detail can be jarring and noticeable to the viewer. To achieve smooth transitions, techniques such as morphing, fading, or cross-fading can be used. These techniques gradually blend between different levels of detail to create a seamless transition. 4.3.2.3 LOD updating. The level of detail of objects needs to be updated dynamically as the camera moves or the objects themselves move within the scene. This can be done by continuously evaluating the distance between the camera and the objects and adjusting the level of detail accordingly. Additionally, LOD can be updated based on the object's importance or relevance to the scene. Objects that are more important or closer to the camera can be assigned higher levels of detail to ensure they are rendered with sufficient quality. 4.3.3 Performance considerations. While LOD can greatly improve rendering performance, there are some considerations to keep in mind when implementing LOD techniques. 4.3.3.1 Artifacts. One challenge in LOD implementation is the potential for visual artifacts. When transitioning between different levels of detail, artifacts such as popping, flickering, or visible changes in geometry or texture quality can occur. These artifacts can be minimized through careful level of detail selection, smooth transitions, and appropriate LOD updating techniques. 4.3.3.2 Memory usage. Implementing LOD may require additional memory to store multiple levels of detail for each object. This can be a concern, especially for large scenes with many objects. Efficient memory management techniques, such as dynamic loading and unloading of LOD data, can help mitigate this issue. 4.3.3.3 Performance impact. While LOD can improve rendering performance, it is important to consider the overall impact on the system's performance. The cost of determining the appropriate level of detail, managing LOD transitions, and updating LOD dynamically can introduce additional computational overhead. Careful optimization and profiling are necessary to ensure that the benefits of LOD outweigh the performance costs. In conclusion, implementing LOD techniques in computer graphics can significantly improve rendering performance by dynamically adjusting the level of detail based on the distance between the camera and objects in the scene. By reducing the complexity of geometry and textures for distant objects, LOD allows for efficient rendering without sacrificing visual quality. However, careful consideration must be given to factors such as level of detail selection, LOD transitions, and performance impact to ensure a seamless and optimized rendering experience. 4.4 Performance considerations. When implementing level of detail LOD techniques in computer graphics, it is crucial to consider the performance implications. While LOD can greatly improve the efficiency of rendering by reducing the number of polygons and textures processed, it also introduces additional complexity that can impact performance. In this section, we will explore some of the performance considerations associated with LOD implementation. 4.4.1 LOD transition costs. One of the primary performance considerations when using LOD is the cost of transitioning between different levels of detail. As an object moves closer or farther from the camera, the LOD system needs to determine when to switch to a higher or lower level of detail. This transition process involves updating the geometry, textures, and shaders associated with the object, which can be computationally expensive. To minimize the performance impact of LOD transitions, it is important to carefully design the LOD system and optimize the transition algorithms. For example, using simple distance-based thresholds for LOD switching can lead to abrupt and noticeable transitions. Instead, more sophisticated techniques such as morphing or blending between LOD levels can provide smoother transitions and reduce visual artifacts. 4.4.2 LOD management and memory usage. Another performance consideration when implementing LOD is the management of LOD data and its impact on memory usage. Each LOD level requires its own set of geometry, textures, and shaders, which can quickly consume significant memory resources, especially for complex scenes with many objects. To optimize memory usage, LOD systems often employ techniques such as level of detail streaming or dynamic LOD loading. These techniques allow for on-demand loading and unloading of LOD data based on the camera's position and visibility. By dynamically managing LOD data, memory usage can be minimized, and performance can be improved. 4.4.3 LOD distance calculation. The calculation of LOD distances is a critical aspect of LOD implementation that directly affects performance. The LOD system needs to determine the appropriate level of detail for each object based on its distance from the camera. However, calculating these distances can be computationally expensive, especially for scenes with a large number of objects. To optimize LOD distance calculations, various techniques can be employed. One common approach is to use hierarchical spatial partitioning structures, such as octrees or quadtrees, to efficiently determine the distance between objects and the camera. Additionally, techniques like frustum culling and occlusion culling can be used to further reduce the number of objects that need to be considered for LOD calculations. 4.4.4 LOD update frequency. The frequency at which LOD levels are updated can also impact performance. Updating LOD levels too frequently can introduce unnecessary overhead, while updating them too infrequently can result in visual artifacts and reduced rendering efficiency. To strike a balance between performance and visual quality, LOD update frequency should be carefully determined based on factors such as object velocity, camera movement, and scene complexity. Adaptive LOD systems that dynamically adjust the update frequency based on these factors can help optimize performance and maintain visual fidelity. 4.4.5 GPU performance considerations. When implementing LOD techniques, it is important to consider the performance implications on the GPU. LOD involves updating geometry, textures, and shaders, which can put a significant load on the GPU's memory bandwidth and processing capabilities. To optimize GPU performance, LOD systems often employ techniques such as batch rendering, where objects with similar LOD levels are grouped together and rendered in a single draw call. This reduces the overhead associated with state changes and improves GPU utilization. Additionally, GPU-specific optimizations such as texture compression, shader instancing, and GPU culling can be employed to further enhance performance when using LOD techniques. Conclusion. In conclusion, while level of detail LOD techniques can greatly improve the performance of computer graphics rendering, they also introduce additional complexity and considerations. By carefully managing LOD transitions, memory usage, LOD distance calculations, update frequency, and GPU performance, developers can optimize the performance of their LOD systems and achieve efficient rendering without sacrificing visual quality. 5. Visibility algorithms. 5.1 Introduction to visibility algorithms. Visibility algorithms play a crucial role in computer graphics by determining which objects or surfaces are visible to the viewer. These algorithms optimize the rendering process by reducing the number of objects that need to be processed, resulting in improved performance and efficiency. Two commonly used visibility algorithms are frustum culling and occlusion culling. 5.1.1 Frustum culling. Frustum culling is a technique used to eliminate objects that are outside the view frustum, which is the portion of the 3D scene that is visible to the camera. The frustum is defined by 6 planes: near, far, left, right, top, and bottom. Any object that lies completely outside these planes is not visible and can be safely discarded from further processing. The process of frustum culling involves determining whether an object's bounding volume intersects with or is completely outside the view frustum. Bounding volumes are simplified geometric shapes, such as spheres or axis-aligned bounding boxes, that encapsulate the object. By performing simple intersection tests between the bounding volumes and the frustum planes, objects that are not visible can be quickly identified and culled. Frustum culling is particularly effective in scenes with a large number of objects, as it reduces the number of objects that need to be processed for rendering. This optimization technique is commonly used in real-time applications, such as video games, where maintaining a high frame rate is essential. 5.1.2 Occlusion culling. Occlusion culling is a technique used to determine which objects or surfaces are occluded, or hidden, from the viewer's perspective. It involves identifying objects or surfaces that are completely or partially obscured by other objects in the scene. By culling occluded objects, the rendering process can focus on rendering only the visible portions of the scene, resulting in significant performance improvements. There are various occlusion culling techniques, including view frustum culling, occlusion queries, and hierarchical occlusion maps. View frustum culling, as discussed earlier, is a form of occlusion culling that eliminates objects outside the view frustum. Occlusion queries involve querying the graphics hardware to determine whether an object is visible or occluded. Hierarchical occlusion maps use a hierarchical data structure to represent the visibility of objects or surfaces, allowing for efficient occlusion culling. Occlusion culling can be challenging to implement, as it requires accurately determining the occlusion relationships between objects in the scene. However, when implemented correctly, it can significantly improve rendering performance, especially in complex scenes with many occluding objects. 5.1.3 Benefits of visibility algorithms. Visibility algorithms, such as frustum culling and occlusion culling, offer several benefits in computer graphics. Improved performance. By eliminating or reducing the processing of non-visible objects or surfaces, visibility algorithms improve rendering performance. This is particularly important in real-time applications where maintaining a high frame rate is crucial. Efficient resource utilization. Visibility algorithms help optimize the use of system resources, such as CPU and GPU, by reducing the workload required for rendering. This allows for better utilization of available resources and can result in smoother and more responsive graphics. Scalability. Visibility algorithms enable efficient rendering of large and complex scenes by selectively rendering only the visible portions. This scalability is essential for applications that need to handle a wide range of scene sizes and complexities. Realism and immersion. By focusing rendering efforts on visible objects or surfaces, visibility algorithms contribute to creating more realistic and immersive graphics. This is particularly important in virtual reality and augmented reality applications, where maintaining a high level of visual fidelity is crucial for a convincing user experience. In conclusion, visibility algorithms, such as frustum culling and occlusion culling, are essential techniques in computer graphics for optimizing the rendering process. These algorithms improve performance, resource utilization, scalability, and contribute to creating more realistic and immersive graphics. Understanding and implementing these algorithms can greatly enhance the efficiency and visual quality of computer graphics applications. 5.2 Backface culling. Backface culling is a technique used in computer graphics to optimize the rendering process by eliminating the rendering of polygons that are not visible to the viewer. It is based on the concept that if a polygon is facing away from the viewer, it will not contribute to the final image and can be safely discarded. 5.2.1 Introduction to backface culling. In computer graphics, 3D objects are represented by polygons, which are flat surfaces defined by a set of vertices. Each polygon has a front face and a back face, determined by the order in which the vertices are defined. The front face is the side that is visible to the viewer, while the back face is the side that is facing away. Backface culling takes advantage of the fact that in most cases, only the front faces of polygons need to be rendered. By identifying and discarding the back faces, the rendering process can be significantly optimized, resulting in improved performance and faster frame rates. 5.2.2 How backface culling works. The process of backface culling involves 3 main steps: determining the orientation of each polygon, calculating the normal vector of each polygon, and comparing the normal vector with the viewing direction. To determine the orientation of a polygon, the order of its vertices is checked. If the vertices are defined in a clockwise order, the polygon is considered to have a front face that is visible to the viewer. If the vertices are defined in a counterclockwise order, the polygon is considered to have a back face that is facing away. The normal vector of a polygon is a vector perpendicular to its surface. It is calculated by taking the cross product of two vectors formed by the polygon's vertices. The direction of the normal vector determines the orientation of the polygon. Once the orientation and normal vector of each polygon are determined, they are compared with the viewing direction. The viewing direction is typically represented by a vector pointing from the viewer's position towards the scene. If the dot product of the normal vector and the viewing direction is negative, it means that the polygon is facing away from the viewer and can be culled. 5.2.3 Implementation of backface culling. Backface culling can be implemented in both software and hardware. In software implementation, the orientation and normal vector of each polygon are calculated and compared with the viewing direction in the CPU. The polygons that fail the culling test are not sent to the graphics pipeline for further processing. In hardware implementation, modern graphics processing units (GPUs) have built-in support for backface culling. The GPU performs the culling test for each polygon in parallel, significantly improving the overall rendering performance. This hardware acceleration allows for real-time rendering of complex scenes with thousands or even millions of polygons. 5.2.4 Performance considerations. Backface culling can greatly improve the performance of a rendering system by reducing the number of polygons that need to be processed. However, there are some considerations to keep in mind when using this technique. One consideration is the accuracy of the culling test. In some cases, due to the complexity of the scene or the presence of transparent objects, the culling test may produce incorrect results. This can lead to visible artifacts or missing geometry in the final image. Careful consideration should be given to the scene setup and the specific requirements of the application to ensure accurate culling. Another consideration is the additional overhead introduced by the culling process itself. While backface culling can save processing time by eliminating unnecessary polygons, the actual culling test adds some computational overhead. This overhead can become significant when dealing with large scenes or when using complex shaders and effects. It is also important to note that backface culling is most effective when combined with other optimization techniques such as frustum culling and occlusion culling. These techniques work together to further reduce the number of polygons that need to be processed, resulting in even greater performance gains. In conclusion, backface culling is a valuable optimization technique in computer graphics that helps improve rendering performance by eliminating the rendering of polygons that are not visible to the viewer. By discarding the back faces of polygons, the rendering process becomes more efficient, resulting in faster frame rates and improved overall performance. However, careful consideration should be given to the scene setup and the specific requirements of the application to ensure accurate culling and to maximize the benefits of this technique. 5.3 Hidden surface removal. Hidden surface removal is a fundamental concept in computer graphics that aims to determine which surfaces or objects in a scene are visible to the viewer and which are hidden behind other objects. This process is crucial for optimizing the rendering pipeline and improving the overall performance of computer graphics applications. 5.3.1 Introduction to hidden surface removal. In computer graphics, a scene is composed of various objects or surfaces that are rendered onto the screen. However, not all of these surfaces are visible to the viewer at any given time. Some surfaces may be completely hidden behind other objects, while others may be partially obscured. Hidden surface removal techniques help identify and eliminate these hidden surfaces, allowing only the visible surfaces to be rendered. The primary goal of hidden surface removal is to reduce the computational workload by eliminating the need to render surfaces that are not visible. By removing hidden surfaces, the rendering process becomes more efficient, resulting in improved performance and faster frame rates. 5.3.2 Depth buffer algorithm. One of the most commonly used techniques for hidden surface removal is the depth buffer algorithm, also known as the Z-buffer algorithm. This algorithm utilizes a depth buffer, also called a Z-buffer, to store the depth values of each pixel in the scene. The depth value represents the distance between the viewer and the surface. During the rendering process, the depth buffer is updated for each pixel based on the depth values of the surfaces being rendered. When a new surface is rendered, its depth value is compared with the value stored in the depth buffer for that pixel. If the new depth value is closer to the viewer, it replaces the existing value in the depth buffer. This ensures that only the closest visible surface is stored in the depth buffer for each pixel. When rendering subsequent surfaces, the depth buffer is checked to determine if the new surface is closer to the viewer than the previously rendered surfaces. If the new surface is closer, it is rendered, and its depth value is updated in the depth buffer. If the new surface is farther away, it is discarded as it is hidden by the previously rendered surface. The depth buffer algorithm is efficient and widely used due to its simplicity and effectiveness in identifying and removing hidden surfaces. However, it requires additional memory to store the depth buffer, and the depth values need to be updated for each pixel during the rendering process, which can impact performance. 5.3.3 Other hidden surface removal techniques. While the depth buffer algorithm is a popular choice for hidden surface removal, there are other techniques that can be used depending on the specific requirements of the application. Some of these techniques include 5.3.3.1 Backface culling. Backface culling is a technique that eliminates the rendering of surfaces that are facing away from the viewer. Each surface in the scene has a normal vector that indicates its orientation. By comparing the angle between the normal vector and the viewer's line of sight, surfaces that are facing away from the viewer can be identified and discarded. This technique is particularly useful for objects that are closed, such as cubes or spheres, where the back faces are never visible. 5.3.3.2 BSP trees. Binary space partitioning (BSP) trees are hierarchical data structures that divide a scene into two regions based on the position of surfaces. Each node in the tree represents a splitting plane that separates the scene into two subspaces. By traversing the BSP tree, surfaces that are hidden behind other surfaces can be quickly identified and discarded, reducing the rendering workload. 5.3.3.3 Portal-based techniques. Portal-based techniques involve dividing a scene into interconnected rooms or areas using portals. Portals or openings are windows that allow visibility between adjacent rooms. By determining which portals are visible from the viewer's current position, surfaces that are hidden behind closed doors or walls can be culled, improving rendering performance. 5.3.4 Performance considerations. When implementing hidden surface removal techniques, it is essential to consider the trade-offs between accuracy and performance. More accurate techniques, such as BSP trees, can provide precise visibility determination but may require additional computational resources and memory. On the other hand, simpler techniques like backface culling may not be as accurate but can offer significant performance benefits. The choice of hidden surface removal technique depends on the specific requirements of the application. Real-time applications, such as video games, often prioritize performance and may opt for simpler techniques like the depth buffer algorithm or backface culling. In contrast, applications that require high visual fidelity, such as architectural visualization, may employ more advanced techniques like BSP trees or portal-based techniques. In conclusion, hidden surface removal is a crucial aspect of computer graphics that helps optimize the rendering process by identifying and eliminating surfaces that are not visible to the viewer. Techniques such as the depth buffer algorithm, backface culling, BSP trees, and portal-based techniques play a vital role in improving performance and enhancing the overall visual quality of computer graphics applications. 5.4 Z-buffer algorithm. The Z-buffer algorithm is a fundamental technique used in computer graphics for hidden surface removal. It is an efficient and widely used method that helps determine which objects or surfaces should be visible in a scene. By utilizing a depth buffer, also known as a Z-buffer, the algorithm compares the depth values of each pixel in the scene to determine the closest visible surface at any given point. 5.4.1 Overview of Z-buffer algorithm. The Z-buffer algorithm works by assigning a depth value to each pixel in the scene. This depth value represents the distance from the viewer's perspective to the corresponding surface. During the rendering process, the algorithm compares the depth value of each pixel with the value stored in the Z-buffer. If the new depth value is closer to the viewer, it replaces the existing value in the Z-buffer and the pixel is rendered. If the new depth value is farther away, it is discarded. 5.4.2 Z-buffer implementation. To implement the Z-buffer algorithm, several steps need to be followed. Initialization. Before rendering the scene, the Z-buffer is initialized with a maximum depth value for each pixel. This ensures that all surfaces will initially be considered as the closest. Rendering. The scene is rendered using any desired rendering technique, such as rasterization or ray tracing. For each pixel, the algorithm calculates the depth value based on the position of the corresponding surface in the scene. Depth comparison. The depth value of each pixel is compared with the value stored in the Z-buffer. If the new depth value is closer, it replaces the existing value in the Z-buffer and the pixel is rendered. Otherwise, the pixel is discarded. Updating the Z-buffer. After rendering each pixel, the Z-buffer is updated with the new depth value if it is closer than the previous value. This ensures that subsequent pixels are correctly compared and rendered. 5.4.3 Advantages of the Z-buffer algorithm. The Z-buffer algorithm offers several advantages that make it a popular choice for hidden surface removal. Efficiency. The Z-buffer algorithm is highly efficient as it only requires a single pass over the scene to determine the visibility of each pixel. This makes it suitable for real-time rendering applications where performance is crucial. Accuracy. The Z-buffer algorithm provides accurate results by considering the depth values of each pixel. It ensures that the closest visible surface is rendered correctly, resulting in realistic and visually appealing scenes. Flexibility. The Z-buffer algorithm can be easily integrated into various rendering techniques, such as rasterization or ray tracing. It can handle complex scenes with multiple overlapping objects and surfaces. Automatic sorting. The Z-buffer algorithm automatically handles the sorting of surfaces based on their depth values. This eliminates the need for manual sorting or complex data structures, simplifying the rendering process. 5.4.4 Limitations and considerations. While the Z-buffer algorithm is a powerful technique, it also has some limitations and considerations that need to be taken into account. Memory requirements. The Z-buffer requires additional memory to store the depth values for each pixel in the scene. The memory requirements increase with the resolution of the rendered image, which can be a concern for real-time applications. Aliasing artifacts. The Z-buffer algorithm can suffer from aliasing artifacts, especially when rendering scenes with thin or small objects. These artifacts can result in jagged edges or flickering surfaces, requiring additional anti-aliasing techniques to mitigate. Overdraw. Overdraw occurs when multiple surfaces are rendered for the same pixel, resulting in wasted computation. The Z-buffer algorithm does not optimize for overdraw, and techniques like early depth testing or hierarchical Z-buffer can be employed to reduce overdraw. Transparency. The Z-buffer algorithm does not handle transparency well. Transparent objects may not be rendered correctly, leading to visual artifacts. Techniques like alpha blending or order-independent transparency can be used in conjunction with the Z-buffer algorithm to address this limitation. 5.4.5 Conclusion. The Z-buffer algorithm is a powerful and widely used technique for hidden surface removal in computer graphics. Its efficiency, accuracy, and flexibility make it suitable for real-time rendering applications. By utilizing a depth buffer, the algorithm determines the closest visible surfaces in a scene, resulting in visually appealing and realistic graphics. However, it is important to consider the limitations and potential issues associated with the Z-buffer algorithm, such as memory requirements, aliasing artifacts, overdraw, and transparency handling. By understanding these considerations, developers can effectively utilize the Z-buffer algorithm to optimize their computer graphics applications. 6. Spatial partitioning. 6.1 Introduction to spatial partitioning. Spatial partitioning is a fundamental technique used in computer graphics to optimize the rendering process by efficiently managing the visibility of objects in a scene. It involves dividing the 3D space into smaller regions or volumes, allowing for faster culling and rendering of objects that are not visible or occluded by other objects. In this section, we will explore the concept of spatial partitioning and its various algorithms, including frustum culling and occlusion culling. These techniques play a crucial role in improving the performance of computer graphics applications by reducing the number of objects that need to be processed and rendered. 6.1.1 Frustum culling. Frustum culling is a technique used to determine which objects in a scene are visible within the camera's view frustum. The view frustum is a truncated pyramid-shaped volume that represents the portion of the 3D space visible to the camera. By performing frustum culling, objects that are outside the frustum can be quickly discarded, saving valuable computational resources. The process of frustum culling involves checking the bounding volumes of objects, such as axis-aligned bounding boxes, AABBs, or spheres, against the frustum planes. If an object's bounding volume is entirely outside any of the frustum planes, it can be safely culled from the rendering process. This reduces the number of objects that need to be processed further, resulting in improved performance. There are several algorithms available for frustum culling, including the bounding sphere test, the bounding box test, and the plane equation test. Each algorithm has its own advantages and trade-offs in terms of accuracy and computational complexity. The choice of algorithm depends on the specific requirements of the application. 6.1.2 Occlusion culling. Occlusion culling is another important technique used in computer graphics to determine which objects are occluded or hidden from view by other objects in a scene. It aims to reduce the rendering workload by excluding objects that are not visible due to occlusion. The process of occlusion culling involves determining the visibility of objects by analyzing the occlusion relationships between them. This can be achieved by using various techniques, such as depth buffer-based occlusion culling, occlusion queries, or hierarchical occlusion maps. Depth buffer-based occlusion culling works by rendering the scene from the camera's viewpoint into a depth buffer. The depth buffer stores the depth values of each pixel in the scene. By comparing the depth values of objects against the depth buffer, occluded objects can be identified and culled from the rendering process. Occlusion queries involve querying the graphics hardware to determine if an object is visible or occluded. This technique can be used in conjunction with other culling methods to improve the accuracy of occlusion culling. Hierarchical occlusion maps divide the scene into a hierarchy of smaller regions and store occlusion information for each region. By traversing the hierarchy, occluded regions can be quickly identified and culled. Occlusion culling can significantly improve the performance of rendering complex scenes with many objects. By excluding occluded objects from the rendering process, the graphics pipeline can focus on rendering only the visible objects, resulting in faster frame rates and improved overall performance. 6.1.3 Benefits of spatial partitioning. Spatial partitioning techniques, such as frustum culling and occlusion culling, offer several benefits in computer graphics applications. Improved performance. By efficiently culling objects that are not visible or occluded, spatial partitioning techniques reduce the computational workload, resulting in improved rendering performance and faster frame rates. Reduced memory usage. By excluding non-visible objects from the rendering process, spatial partitioning techniques reduce the memory requirements for storing object data, allowing for more efficient memory utilization. Scalability. Spatial partitioning techniques can handle scenes with a large number of objects by selectively rendering only the visible or occluded objects, ensuring smooth rendering performance even in complex scenes. Flexibility. Spatial partitioning techniques can be combined with other optimization techniques, such as level of detail (LOD) and visibility algorithms, to further enhance rendering performance and visual quality. In conclusion, spatial partitioning techniques, including frustum culling and occlusion culling, are essential tools in the optimization of computer graphics applications. By efficiently managing the visibility of objects in a scene, These techniques improve rendering performance, reduce memory usage, and enable the rendering of complex scenes with high efficiency. 6.2 Bounding volume hierarchy. In computer graphics, one of the key challenges is to efficiently determine which objects or parts of objects are visible within a given view frustum. This process, known as culling, helps optimize rendering by eliminating unnecessary computations for objects that are not visible. Bounding volume hierarchy (BVH) is a spatial partitioning technique commonly used in computer graphics to accelerate the culling process. 6.2.1 Introduction to bounding volume hierarchy. Bounding volume hierarchy is a hierarchical data structure that organizes objects in a scene into a tree-like structure. Each node in the tree represents a bounding volume that encloses a group of objects or other bounding volumes. The root node of the tree represents the entire scene, and the leaf nodes represent individual objects or groups of objects. The main idea behind BVH is to exploit the spatial coherence of objects in a scene. Objects that are close to each other in space are likely to be visible or occluded together. By grouping these objects into bounding volumes, we can quickly determine if an entire group of objects is visible or occluded, without having to check each object individually. 6.2.2 Construction of bounding volume hierarchy. The construction of a BVH involves recursively partitioning the scene into smaller bounding volumes until a termination condition is met. There are several algorithms for constructing BVH, but one common approach is the top-down construction method. In the top-down construction method, the scene is initially enclosed in a single bounding volume, typically an axis-aligned bounding box (AABB). This bounding volume is then recursively split into two child bounding volumes along a chosen splitting plane. The splitting plane is determined based on some criteria, such as maximizing the spatial coherence or minimizing the overlap between child bounding volumes. The splitting process continues until a termination condition is met. This condition can be based on a maximum depth of the tree, a minimum number of objects per leaf node, or a combination of both. Once the termination condition is reached, the leaf nodes are created, each containing a subset of objects from the scene. 6.2.3 Traversal of bounding volume hierarchy. Once the BVH is constructed, it can be traversed to determine the visibility of objects within a given view frustum. The traversal process starts at the root node and recursively descends through the tree, visiting only the nodes that intersect with the view frustum. During traversal, several tests are performed to determine if a node is visible, occluded, or partially visible. These tests involve comparing the bounding volume of a node with the view frustum and can be efficiently performed using various intersection tests, such as AABB frustum intersection tests. If a node is determined to be fully visible, all the objects within that node are considered visible and can be rendered. If a node is determined to be occluded, none of the objects within that node need to be rendered. If a node is partially visible, the traversal continues to its child nodes until the leaf nodes are reached. 6.2.4 Benefits and limitations of bounding volume hierarchy. Bounding volume hierarchy offers several benefits in terms of optimizing the culling process in computer graphics. By grouping objects into bounding volumes, the number of intersection tests required during traversal is significantly reduced, leading to improved rendering performance. BVH also allows for efficient occlusion culling, as entire groups of objects can be quickly determined to be occluded. However, BVH construction and traversal do come with some overhead. The construction process requires additional computational resources to partition the scene and create the tree structure. The traversal process also incurs some overhead due to the recursive nature of the algorithm. Additionally, BVH is not suitable for dynamic scenes where objects frequently move or change their positions, as the tree structure needs to be rebuilt or updated accordingly. Despite these limitations, BVH remains a widely used technique in computer graphics due to its effectiveness in reducing the computational complexity of the culling process. It is often combined with other culling techniques, such as frustum culling and occlusion culling, to further improve rendering performance in real-time applications. Overall, bounding volume hierarchy provides a powerful tool for optimizing the visibility determination process in computer graphics, enabling efficient rendering of complex scenes while minimizing unnecessary computations. 6.3 Octrees. In computer graphics, spatial partitioning techniques are used to efficiently organize and manage the objects in a scene. One such technique is the use of octrees, which provide a hierarchical representation of 3D space. Octrees are particularly useful for frustum culling and occlusion culling, as they allow for quick and accurate determination of which objects are visible or potentially visible in a given view frustum. 6.3.1 Overview of octrees. An octree is a tree data structure where each internal node has exactly 8 children, corresponding to the 8 octants of 3D space. The root node represents the entire 3D space, and each subsequent level of the tree further subdivides the space into smaller octants. This hierarchical structure allows for efficient spatial querying and traversal. The octree is constructed by recursively subdividing the space until a termination condition is met. This termination condition is typically based on a maximum depth or a minimum size threshold. At each level of the tree, the space is divided into 8 equal-sized octants, and objects are assigned to the appropriate octants based on their position. This process continues until the termination condition is reached, resulting in a tree structure that represents the spatial occupancy of the scene. 6.3.2 Frustum culling with octrees. Frustum culling is a technique used to eliminate objects that are outside the view frustum, which is the portion of 3D space visible to the camera. Octrees provide an efficient way to perform frustum culling by exploiting the hierarchical structure of the tree. To perform frustum culling with octrees, the view frustum is recursively tested against the octants of the tree. If an octant is completely outside the frustum, it can be safely discarded along with all its child octants. If an octant is partially inside the frustum, further subdivision is necessary to determine which child octants are potentially visible. This process continues until the termination condition is met or until all potentially visible objects are identified. By using octrees for frustum culling, the number of objects that need to be processed and rendered can be significantly reduced, resulting in improved performance. The hierarchical nature of octrees allows for efficient traversal and pruning of the scene, making frustum culling an essential optimization technique in real-time computer graphics. 6.3.3 Occlusion culling with octrees. Occlusion culling is a technique used to determine which objects are occluded or hidden from view by other objects in the scene. Octrees can be utilized to perform occlusion culling by exploiting the spatial relationships between objects. To perform occlusion culling with octrees, the visibility of each octant is determined based on occlusion tests. Occlusion tests involve checking if an octant is completely occluded by other objects in the scene. If an octant is found to be occluded, it can be safely discarded along with all its child octants. If an octant is potentially visible, further subdivision is necessary to determine which child octants are occluded or visible. This process continues until the termination condition is met or until all occluded objects are identified. Occlusion culling with octrees can greatly reduce the number of objects that need to be rendered, resulting in significant performance improvements. By efficiently determining which objects are occluded, unnecessary rendering operations can be avoided, leading to faster frame rates and more efficient resource utilization. 6.3.4 Performance considerations. While octrees provide an efficient spatial partitioning technique for frustum culling and occlusion culling, there are some performance considerations to keep in mind. One consideration is the construction time of the octree. The process of recursively subdividing the space and assigning objects to octants can be computationally expensive, especially for complex scenes with a large number of objects. However, this cost is typically incurred only once during the initialization phase, and the resulting octree can be reused for subsequent frame rendering. Another consideration is the memory overhead of storing the octree. The hierarchical structure of the octree requires additional memory compared to a flat list of objects. The memory usage increases with the depth of the tree and the number of objects in the scene. However, the memory overhead is often outweighed by the performance benefits of efficient frustum culling and occlusion culling. Additionally, the efficiency of frustum culling and occlusion culling with octrees depends on the spatial distribution of objects in the scene. If objects are evenly distributed throughout the space, the octree can provide a balanced and efficient representation. However, if objects are clustered or concentrated in certain regions, the octree may become unbalanced, leading to suboptimal performance. In conclusion, octrees are a powerful spatial partitioning technique that can be used for frustum culling and occlusion culling in computer graphics. By exploiting the hierarchical structure of the tree, octrees enable efficient determination of visible and occluded objects, resulting in improved rendering performance. However, careful consideration should be given to the construction time, memory overhead, and spatial distribution of objects to ensure optimal performance. 6.4 Quad trees. In computer graphics, spatial partitioning techniques are essential for optimizing rendering performance. One such technique is the use of quad trees, which provide an efficient way to organize and manage spatial data. Quad trees are particularly useful for frustum culling and occlusion culling, two important optimization techniques in computer graphics. 6.4.1 Introduction to quad trees. A quad tree is a tree data structure in which each internal node has exactly 4 children. The root node represents the entire space, and each subsequent level of the tree divides the space into 4 quadrants. This recursive subdivision continues until the desired level of detail is achieved or until a termination condition is met. Quad trees are commonly used to represent two-dimensional spaces, such as a screen or a terrain. Each node in the quad tree represents a rectangular region of the space, and the tree structure allows for efficient spatial queries and operations. 6.4.2 Quad tree construction. The construction of a quad tree involves recursively subdividing the space until a termination condition is met. The termination condition can be based on factors such as the maximum depth of the tree, the size of the region, or the number of objects contained within a region. To construct a quad tree, the initial space is represented by the root node. The space is then divided into 4 quadrants, and each quadrant becomes a child node of the root. This process is repeated for each child node until the termination condition is met. 6.4.3 Quad tree representation. Each node in a quad tree contains information about the region it represents and the objects contained within that region. This information can be stored in various ways, depending on the specific requirements of the application. One common approach is to store the objects directly in the leaf nodes of the quad tree. This allows for efficient retrieval of objects within a specific region. Another approach is to store references to the objects in the leaf nodes, while the actual objects are stored in a separate data structure. 6.4.4 Frustum culling with quad trees. Frustum culling is a technique used to determine which objects in a scene are visible within the viewing frustum. The viewing frustum is the portion of the space that is visible to the camera. Quad trees can be used to perform frustum culling efficiently. The quad tree is traversed recursively, and at each node, a test is performed to determine if the node's region intersects with the viewing frustum. If the region is completely outside the frustum, the traversal can be terminated for that node and its children. If the region is partially or fully inside the frustum, the traversal continues to the child nodes. By using quad trees for frustum culling, the number of objects that need to be processed for rendering can be significantly reduced. This leads to improved rendering performance, especially in scenes with a large number of objects. 6.4.5 Occlusion culling with quad trees. Occlusion culling is a technique used to determine which objects in a scene are occluded or hidden from view by other objects. This is particularly useful in complex scenes where objects can obstruct each other. Quad trees can also be utilized for occlusion culling. The quad tree is traversed recursively, and at each node, a test is performed to determine if the node's region is occluded by other objects. If the region is completely occluded, the traversal can be terminated for that node and its children. If the region is partially or fully visible, the traversal continues to the child nodes. Occlusion culling with quad trees can greatly reduce the number of objects that need to be rendered, resulting in improved rendering performance. By avoiding the rendering of occluded objects, unnecessary computations can be avoided, leading to faster frame rates and more efficient use of system resources. 6.4.6 Performance considerations with quad trees. While quad trees offer significant benefits in terms of spatial partitioning and culling, there are some performance considerations to keep in mind. One consideration is the construction time of the quad tree. The recursive subdivision process can be computationally expensive, especially for large spaces or complex scenes. It is important to balance the level of detail required with the construction time to achieve optimal performance. Another consideration is the memory overhead of storing the quad tree data structure. The quad tree requires additional memory to store the tree nodes and their associated data. This overhead should be taken into account when considering the memory requirements of the application. Additionally, the efficiency of frustum culling and occlusion culling with quad trees depends on the spatial distribution of objects in the scene. If the objects are evenly distributed, the benefits of quad trees are maximized. However, if the objects are clustered or concentrated in certain regions, the effectiveness of quad trees may be reduced. In conclusion, quad trees are a powerful spatial partitioning technique that can be used for frustum culling and occlusion culling in computer graphics. By efficiently organizing and managing spatial data, quad trees can significantly improve rendering performance and optimize the use of system resources. However, careful consideration should be given to the construction time, memory overhead, and spatial distribution of objects to achieve optimal performance. 7. Lighting and shadows. 7.1 Introduction to lighting and shadows. Lighting and shadows play a crucial role in computer graphics, as they contribute to the realism and visual appeal of rendered scenes. By simulating the behavior of light in a virtual environment, we can create the illusion of depth, shape, and texture. In this section, we will explore the fundamental concepts of lighting and shadows, as well as the techniques used to implement them in computer graphics. 7.1.1 Lighting models. To understand lighting in computer graphics, we need to consider how light interacts with objects in the real world. Light can be emitted from a source, such as the sun or a light bulb, and it can also be reflected, refracted, or absorbed by objects. To simulate these interactions, lighting models are used. A lighting model describes how light interacts with a surface and determines its appearance. One commonly used lighting model is the Phong lighting model, which consists of three components: ambient, diffuse, and specular. The ambient component represents the light that is scattered and reflected by the environment, providing a base level of illumination to all objects in the scene. The diffuse component simulates the light that is scattered equally in all directions by a rough surface, resulting in a uniform illumination. The specular component represents the light that is reflected in a concentrated manner by a smooth surface, creating highlights and shiny reflections. By combining these three components, we can calculate the final color of a pixel based on its surface properties and the position of the light source. This process is known as shading, and it is essential for creating realistic lighting effects in computer graphics. 7.1.2 Shadow mapping. Shadows are an integral part of realistic rendering, as they provide depth and dimension to a scene. Shadow mapping is a widely used technique for generating shadows in computer graphics. The basic idea behind shadow mapping is to determine whether a point in the scene is in shadow or not. This is achieved by rendering the scene from the perspective of the light source and storing the depth values of the visible surfaces in a texture called the shadow map. During the final rendering pass, the depth values of the scene are compared with the values stored in the shadow map to determine if a point is in shadow or not. To improve the quality of the shadows, techniques such as percentage closer filtering (PCF) can be applied. PCF takes multiple samples around a pixel and calculates the average depth value, resulting in smoother and more realistic shadows. Shadow mapping is a relatively efficient technique for generating shadows in real-time applications, but it has some limitations. One limitation is the occurrence of aliasing artifacts, which can cause jagged edges or pixelated shadows. This can be mitigated by increasing the resolution of the shadow map or by using techniques such as cascaded shadow maps. 7.1.3 Shadow volume. Another technique for generating shadows is the shadow volume algorithm. Unlike shadow mapping, which works at the pixel level, shadow volumes operate at the object level. The shadow volume algorithm works by extruding the silhouette edges of an object towards the light source to create a volume that represents the shadow cast by the object. By intersecting this volume with the scene geometry, we can determine which parts of the scene are in shadow. The shadow volume algorithm requires the scene geometry to be closed and manifold, meaning that there are no holes or self-intersections. It also requires the light source to be a point light or a directional light. While the shadow volume algorithm can produce accurate shadows, it can be computationally expensive, especially for complex scenes with many objects. To optimize the algorithm, techniques such as hierarchical shadow volumes or stencil buffer optimizations can be employed. 7.1.4 Performance considerations. Implementing lighting and shadows in computer graphics can be computationally expensive, especially in real-time applications where performance is crucial. Therefore, it is essential to consider performance optimizations to ensure smooth and responsive rendering. One common optimization technique is to use pre-computed lighting data. By pre-computing the lighting information for static objects or environments, we can reduce the computational cost during runtime. This approach is commonly used in games and virtual reality applications. Another optimization technique is to use simplified lighting models or approximations. Instead of using complex lighting models, simpler models can be used to achieve similar visual effects with less computational overhead. This trade-off between visual fidelity and performance is often necessary in real-time rendering. Furthermore, techniques such as level of detail (LOD) and occlusion culling can be employed to reduce the number of objects that need to be considered for lighting and shadow calculations. By dynamically adjusting the level of detail based on the distance from the camera or by culling objects that are not visible, we can significantly improve performance without sacrificing visual quality. In conclusion, lighting and shadows are essential components of computer graphics that contribute to the realism and visual appeal of rendered scenes. By understanding the fundamental concepts and implementing efficient techniques such as shadow mapping and shadow volumes, we can achieve realistic lighting effects. However, it is crucial to consider performance optimizations to ensure smooth and responsive rendering in real-time applications. 7.2 Lighting models. Lighting plays a crucial role in computer graphics as it helps create realistic and visually appealing scenes. In order to achieve this, various lighting models are used to simulate the behavior of light in the virtual environment. These models take into account factors such as the position and intensity of light sources, the properties of the materials being illuminated, and the interaction between light and surfaces. 7.2.1 Ambient lighting. Ambient lighting is a basic lighting model that simulates the indirect lighting in a scene. It represents the light that is scattered and reflected multiple times, resulting in a uniform illumination across the entire scene. Ambient lighting is often used to provide a base level of illumination and to prevent completely dark areas in the absence of direct light sources. It is typically represented by a constant color or intensity value. 7.2.2 Diffuse lighting. Diffuse lighting is a lighting model that simulates the way light scatters and reflects off rough surfaces. It is based on Lambert's law, which states that the intensity of light reflected from a surface is proportional to the cosine of the angle between the surface normal and the direction of the incident light. This means that surfaces facing the light source directly will appear brighter, while surfaces facing away from the light source will appear darker. Diffuse lighting is commonly used to simulate the appearance of matte or non-reflective surfaces. 7.2.3 Specular lighting. Specular lighting is a lighting model that simulates the way light reflects off shiny or glossy surfaces. It is based on the observation that light reflects more strongly in certain directions, known as the specular reflection direction. The intensity of the specular reflection depends on the angle between the direction of the incident light and the direction of the viewer's line of sight, as well as the surface's shininess or roughness. Specular lighting is used to create highlights on surfaces, giving them a polished or reflective appearance. 7.2.4 Phong lighting model. The Phong lighting model combines ambient, diffuse, and specular lighting to create a more realistic representation of how light interacts with surfaces. It was introduced by Bui Tuong Phong in 1975 and has since become one of the most widely used lighting models in computer graphics. The Phong model calculates the total intensity of light at each point on a surface by summing the contributions from ambient, diffuse, and specular lighting components. This model allows for the simulation of a wide range of materials, from dull and rough surfaces to highly reflective and shiny surfaces. 7.2.5 Blin Phong lighting model. The Blin Phong lighting model is an extension of the Phong lighting model that introduces a modified specular term. It was proposed by James F. Blin in 1977 as a more efficient alternative to the original Phong model. The Blin Phong model replaces the calculation of the specular reflection direction with the halfway vector between the direction of the incident light and the direction of the viewer's line of sight. This modification simplifies the calculations while still producing visually pleasing results. The Blin Phong model is widely used in real-time rendering applications due to its simplicity and efficiency. 7.2.6 Other lighting models. In addition to the Phong and Blin Phong models, there are several other lighting models that have been developed to simulate specific lighting phenomena or to achieve specific visual effects. Some examples include the Cook-Torrance model, which is used to simulate the appearance of metallic surfaces, and the Oren-Nair model, which is used to simulate the appearance of rougher textured surfaces. These models take into account additional factors such as surface roughness, microfacet distribution, and light scattering to create more accurate and realistic lighting effects. Overall, lighting models are essential tools in computer graphics for creating visually appealing and realistic scenes. By simulating the behavior of light and its interaction with surfaces, these models allow for the creation of stunning visual effects in immersive virtual environments. The choice of lighting model depends on the specific requirements of the application and the desired visual style, with each model offering its own advantages and limitations. 7.3 Shadow Mapping. Shadow mapping is a widely used technique in computer graphics to simulate the casting and rendering of shadows in a scene. Shadows play a crucial role in creating realistic and immersive visual experiences, as they provide depth and enhance the perception of objects in a three-dimensional environment. By accurately rendering shadows, we can add depth, realism, and visual cues to the scene, making it more visually appealing and believable. 7.3.1 Introduction to Shadow Mapping. Shadow mapping is a technique that involves rendering a scene from the perspective of a light source to create a depth map, known as a shadow map. This shadow map is then used during the final rendering pass to determine which areas of the scene are in shadow and should be darkened. The process involves comparing the depth values of the shadow map with the depth values of the objects in the scene to determine if a pixel is in shadow or not. The basic idea behind shadow mapping is to determine if a point in the scene is visible from the light source's perspective. If it is not visible, then it is in shadow. To achieve this, we render the scene from the light's point of view and store the depth values of the objects in a texture known as the shadow map. During the final rendering pass, we compare the depth value of each pixel with the corresponding value in the shadow map. If the depth value is greater, it means that the pixel is in shadow and should be darkened. 7.3.2 Shadow Mapping Techniques. There are several techniques and variations of shadow mapping that have been developed over the years to improve the quality and performance of shadow rendering. Some of the commonly used techniques include 7.3.2.1 Basic Shadow Mapping. The basic shadow mapping technique involves rendering the scene from the light's perspective and storing the depth values in a shadow map. During the final rendering pass, the depth values of the pixels are compared with the corresponding values in the shadow map to determine if they are in shadow or not. This technique is relatively simple to implement but can suffer from aliasing and self-shadowing artifacts. 7.3.2.2 Percentage Closer Filtering (PCF). PCF is a technique used to reduce the aliasing artifacts caused by the discrete nature of shadow maps. It involves sampling multiple points within the shadow map and averaging their depth values to determine if a pixel is in shadow or not. By taking multiple samples, PCF can produce smoother and more accurate shadows, but it comes at the cost of increased computational complexity. 7.3.2.3 Variance Shadow Mapping (VSM). Variance shadow mapping is an extension of the basic shadow mapping technique that aims to reduce the blocky and pixelated appearance of shadows. Instead of storing the depth values in the shadow map, VSM stores the variance of the depth values. This variance information is then used during the final rendering pass to calculate the probability of a pixel being in shadow. VSM can produce softer and more realistic shadows, but it requires additional computations and memory. 7.3.2.4 Exponential Shadow Mapping (ESM). ESM is another technique that addresses the blocky appearance of shadows in basic shadow mapping. It involves storing the logarithm of the depth values in the shadow map instead of the actual depth values. During the final rendering pass, the logarithmic depth values are converted back to linear space and compared with the depth values of the pixels to determine if they are in shadow or not. ESM can produce smoother and more natural-looking shadows, but it also requires additional computations. 7.3.3 Implementation of Shadow Mapping. Implementing shadow mapping involves several steps, including setting up the shadow map, rendering the scene from the light's perspective, and performing the final rendering pass using the shadow map. The process can be summarized as follows. Create a depth texture to serve as the shadow map. Set up a camera or light source to render the scene from the desired perspective. Render the scene from the light's perspective and store the depth values in the shadow map. During the final rendering pass, sample the depth values from the shadow map and compare them with the depth values of the pixels to determine if they are in shadow or not. Apply appropriate shading and lighting calculations to the pixels based on their shadow status. It is important to note that shadow mapping can introduce various artifacts, such as aliasing, self-shadowing, and light bleeding. These artifacts can be mitigated through techniques like PCF, VSM, and ESM, as mentioned earlier. 7.3.4 Performance Considerations. Shadow mapping can be computationally expensive, especially when rendering complex scenes with multiple light sources and high-resolution shadow maps. To optimize the performance of shadow mapping, several techniques can be employed. Shadow map resolution. Lowering the resolution of the shadow map can significantly reduce the computational cost. However, this may result in lower quality and more noticeable artifacts. Culling. Applying frustum culling and occlusion culling techniques can help reduce the number of objects that need to be rendered and processed for shadow mapping. Level of detail (LOD). Using lower LOD models for objects in the shadow map can reduce the number of vertices and triangles that need to be processed, improving performance. Parallelization. Utilizing parallel processing techniques, such as multi-threading or GPU compute shaders, can distribute the workload and improve the overall performance of shadow mapping. By carefully considering these performance considerations and implementing appropriate optimizations, shadow mapping can be efficiently used to enhance the visual quality of computer graphics applications without sacrificing performance. In conclusion, shadow mapping is a powerful technique for simulating shadows in computer graphics. By rendering a scene from the perspective of a light source and comparing depth values, shadow mapping can create realistic and immersive visual experiences. Various techniques, such as PCF, VSM, and ESM, can be employed to improve the quality of shadows. However, shadow mapping can be computationally expensive, and careful consideration of performance optimizations is necessary to achieve real-time rendering in complex scenes. 7.4 Shadow Volume. In computer graphics, shadows play a crucial role in creating realistic and immersive scenes. They add depth, dimension, and a sense of realism to the rendered images. One popular technique used to generate shadows is the shadow volume algorithm. This algorithm is based on the concept of frustum culling and occlusion culling, which we have discussed in previous chapters. 7.4.1 Introduction to Shadow Volume. Shadow volume is a technique used to calculate and render shadows in real-time graphics. It is based on the concept of extruding the silhouette edges of an object to create a volume that represents the shadow cast by the object. This volume is then intersected with the scene geometry to determine the areas that are in shadow. The shadow volume algorithm works by first determining which objects are potentially casting shadows on a given surface. This is done using frustum culling techniques, which involve checking if the objects are within the view frustum of the camera. Once the potentially shadow-casting objects are identified, the algorithm proceeds to calculate the silhouette edges of these objects. 7.4.2 Calculating Silhouette Edges. To calculate the silhouette edges, the shadow volume algorithm uses the concept of occlusion culling. Occlusion culling involves determining which parts of an object are visible from a particular viewpoint. In the case of shadow volume, occlusion culling is used to identify the edges of the object that are visible from the light source's perspective. The algorithm starts by rendering the scene from the light source's viewpoint, creating a depth buffer that stores the depth values of the visible surfaces. Then, for each potentially shadow-casting object, the algorithm checks if any of its vertices are closer to the light source than the corresponding depth values in the depth buffer. If a vertex is closer, it means that the corresponding edge is visible from the light source's perspective and is part of the silhouette. Once the silhouette edges are identified, the algorithm extrudes them to create the shadow volume. This is done by extending the edges to infinity in the direction opposite to the light source. The resulting volume represents the region where the shadow is cast. 7.4.3 Rendering shadows. After the shadow volume is constructed, the next step is to render the shadows on the scene geometry. This is done by intersecting the shadow volume with the scene geometry. The algorithm determines which parts of the scene geometry are inside the shadow volume and applies a shadowing effect to those areas. To perform the intersection, the algorithm uses the stencil buffer. The stencil buffer is a separate buffer that stores integer values for each pixel on the screen. The algorithm first clears the stencil buffer and then renders the shadow volume, incrementing the stencil value for each pixel that is inside the shadow volume. Next, the algorithm renders the scene geometry, but this time it only updates the pixels that have a stencil value greater than 0. These pixels are the ones that are inside the shadow volume and should be shadowed. The algorithm applies a shadowing effect to these pixels, typically by darkening their color or reducing their intensity. 7.4.4 Performance Considerations. While the shadow volume algorithm can produce high-quality shadows, it is computationally expensive and can have a significant impact on performance. The main performance bottleneck is the calculation of the silhouette edges and the extrusion of the shadow volume. These operations require additional geometry processing and can be time-consuming, especially for complex scenes with many objects. To mitigate the performance impact, several optimization techniques can be applied. One common optimization is to use simplified representations of the objects for silhouette edge calculation. This can involve using lower polygon models or precomputed simplified meshes specifically designed for shadow volume generation. Another optimization technique is to limit the number of shadow volumes rendered. This can be achieved by using hierarchical structures, such as bounding volume hierarchies or spatial partitioning techniques, to quickly determine which objects are potentially casting shadows on a given surface. By reducing the number of shadow volumes, the algorithm can save processing time and improve performance. Additionally, hardware acceleration techniques, such as using the GPU's programmable shaders, can be employed to offload some of the computation to the graphics hardware. This can significantly speed up the silhouette edge calculation and shadow volume extrusion, resulting in improved performance. In conclusion, the shadow volume algorithm is a powerful technique for generating realistic shadows in real-time graphics. By leveraging the concepts of frustum culling and occlusion culling, it can accurately calculate and render shadows in a scene. However, due to its computational complexity, careful optimization is necessary to ensure acceptable performance in real-time applications. 8. Texture mapping. 8.1 Introduction to texture mapping. Texture mapping is a fundamental technique in computer graphics that allows for the realistic rendering of surfaces by applying images, called textures, onto 3D objects. It adds detail, color, and texture to objects, enhancing their visual appearance and making them more visually appealing and realistic. Texture mapping is widely used in various applications, including video games, virtual reality, architectural visualization, and product design. 8.1.1 What is texture mapping? Texture mapping involves the process of wrapping a 2D image, called a texture map, onto a 3D object's surface. The texture map contains pixel values that represent the color and surface properties of the object. By mapping the texture onto the object, the appearance of the object can be enhanced, giving it the illusion of depth, surface roughness, and intricate details. The texture map is typically created using image editing software or generated procedurally. It can be a photograph, a hand-drawn image, or a computer-generated pattern. The texture map is then applied to the object's surface using texture coordinates. 8.1.2 Texture coordinates. Texture coordinates are used to specify how the texture map is mapped onto the object's surface. They define a correspondence between points on the object's surface and points on the texture map. Each vertex of the object's geometry is assigned a set of texture coordinates that determine which part of the texture map should be applied to that vertex. Texture coordinates are usually defined in the range of 0, 1 for both the horizontal u and vertical v directions. These coordinates are interpolated across the surface of the object during rendering, ensuring that the texture is smoothly applied to the entire surface. 8.1.3 Texture filtering. Texture filtering is a technique used to improve the visual quality of texture mapping by reducing artifacts such as aliasing and blurring. When a texture is applied to a surface, the texture coordinates may not align perfectly with the pixels of the texture map, resulting in sampling errors. Texture filtering algorithms help to minimize these errors and produce a smoother and more visually pleasing result. There are several texture filtering techniques commonly used in computer graphics. 8.1.3.1 Nearest neighbor filtering. Nearest neighbor filtering is the simplest and fastest texture filtering algorithm. It selects the pixel from the texture map that is closest to the texture coordinates of the current fragment. This method can produce blocky or pixelated results, especially when the texture is magnified or minified. 8.1.3.2 Bilinear filtering. Bilinear filtering is a more advanced texture filtering algorithm that takes into account the neighboring pixels of the texture coordinates. It calculates the weighted average of the 4 nearest pixels in the texture map to determine the color of the current fragment. Bilinear filtering produces smoother results compared to nearest neighbor filtering and is suitable for most applications. 8.1.3.3 Trilinear filtering. Trilinear filtering is an extension of bilinear filtering that addresses the issue of texture aliasing when objects are viewed from different distances. It combines bilinear filtering with MIP mapping, which is the precomputed set of texture maps at different levels of detail. Trilinear filtering selects the appropriate MIP level based on the distance between the object and the camera, ensuring that the texture maintains its quality and detail regardless of the viewing distance. 8.1.4 Texture compression. Texture compression is a technique used to reduce the memory footprint of texture maps without significant loss of visual quality. It is particularly important in real-time graphics applications where memory bandwidth and storage space are limited. There are various texture compression algorithms available, each with its own trade-offs between compression ratio and visual quality. Some popular texture compression formats include S3TC, also known as DXT, ETC, Ericsson texture compression, and ASTC, adaptive scalable texture compression. Texture compression algorithms exploit the spatial redundancy in texture maps to reduce the number of bits required to store the texture data. They achieve this by using various compression techniques such as block-based compression, color quantization, and entropy coding. Texture compression not only reduces the memory footprint but also improves rendering performance by reducing memory bandwidth requirements. Compressed textures can be efficiently loaded into the graphics hardware and decompressed on the fly during rendering. In conclusion, texture mapping is a powerful technique in computer graphics that enhances the visual appearance of 3D objects by applying images onto their surfaces. Texture coordinates, texture filtering, and texture compression are essential components of texture mapping that contribute to the realistic rendering of objects in real-time graphics applications. Understanding these concepts and their implementation is crucial for optimizing the performance and visual quality of computer graphics systems. 8.2 Texture coordinates. Texture mapping is a fundamental technique in computer graphics that allows us to apply images, called textures, onto the surfaces of 3D objects. By mapping the 2D texture coordinates to the 3D geometry, we can create realistic and detailed surfaces that enhance the visual quality of computer-generated images. In this section, we will explore the concept of texture coordinates and their role in texture mapping. 8.2.1 Introduction to texture coordinates. Texture coordinates are a set of 2D coordinates that define how a texture is mapped onto a 3D object. They provide a mapping between the vertices of the object's geometry and the corresponding points on the texture image. Each vertex of the object is assigned a texture coordinate, which determines the position on the texture that will be applied to that vertex. The texture coordinates are usually defined in a normalized coordinate system, where the range of values for both the u horizontal and v vertical coordinates is between 0 and 1. These normalized coordinates allow textures of any size to be applied to objects without distortion. The texture coordinates can be stored as additional vertex attributes or computed on the fly during the rendering process. 8.2.2 Texture Coordinate Generation. There are several methods for generating texture coordinates for a 3D object. The choice of method depends on the shape and complexity of the object, as well as the desired texture mapping effect. Here are some commonly used techniques. 8.2.2.1 Planar Mapping. Planar mapping is a simple texture coordinate generation technique that projects the texture onto the object as if it were wrapped around a flat plane. This method is suitable for objects with planar surfaces, such as walls or floors. The texture coordinates are calculated based on the position of the vertices relative to the plane. 8.2.2.2 Cylindrical Mapping. Cylindrical mapping is used for objects with cylindrical or circular surfaces, such as columns or barrels. The texture coordinates are generated by projecting the texture onto the object as if it were wrapped around a cylinder. The U coordinate is determined by the angle around the cylinder, while the V coordinate is based on the height of the vertex. 8.2.2.3 Spherical Mapping. Spherical mapping is commonly used for objects with spherical or curved surfaces, such as spheres or globes. The texture coordinates are calculated by projecting the texture onto the object as if it were wrapped around a sphere. The U coordinate is determined by the longitude angle, while the V coordinate is based on the latitude angle. 8.2.2.4 UV Mapping. UV mapping is a versatile technique that allows for more complex and precise texture mapping. It involves manually assigning texture coordinates to each vertex of the object. This method provides full control over the placement and orientation of the texture on the object's surface. UV mapping is widely used in applications where accurate texture alignment is required, such as character modeling and game development. 8.2.3 Texture Coordinate Interpolation. Once the texture coordinates are assigned to the vertices of the object, the texture mapping process involves interpolating the coordinates across the surface of the object's polygons. This interpolation ensures that the texture is smoothly applied to the entire surface, even if the polygons are irregularly shaped. The interpolation of texture coordinates can be performed using various algorithms, such as bilinear interpolation or perspective correct interpolation. These algorithms take into account the position and orientation of the polygons in 3D space to accurately determine the texture coordinates for each pixel on the polygon's surface. 8.2.4 Texture Coordinate Wrapping. Texture coordinate wrapping determines how the texture coordinates outside the range of 0 to 1 are handled. There are several wrapping modes available, including 8.2.4.1 Repeat. In the repeat mode, the texture is repeated or tiled when the texture coordinates exceed the range of 0 to 1. This creates a seamless pattern of the texture across the surface of the object. 8.2.4.2 Clamp. In the clamp mode, the texture coordinates are clamped to the range of 0 to 1. Any texture coordinates outside this range are set to the nearest valid coordinate. This mode prevents the texture from repeating and creates a border effect at the edges of the object. 8.2.4.3 Mirror. In the mirror mode, the texture is mirrored when the texture coordinates exceed the range of 0 to 1. This creates a symmetrical pattern of the texture across the surface of the object. 8.2.5 Texture Coordinate Manipulation. Texture coordinates can be manipulated to achieve various effects in texture mapping. Some common techniques include 8.2.5.1 Texture Scaling. Texture scaling involves scaling the texture coordinates to control the size of the texture on the object's surface. This can be used to create textures that appear larger or smaller on different parts of the object. 8.2.5.2 Texture Translation. Texture translation involves shifting the texture coordinates to control the position of the texture on the object's surface. This can be used to create textures that appear to be moving or sliding across the object. 8.2.5.3 Texture Rotation. Texture rotation involves rotating the texture coordinates to control the orientation of the texture on the object's surface. This can be used to create textures that appear to be rotated or tilted. 8.2.6 Conclusion. Texture coordinates play a crucial role in texture mapping, allowing us to apply textures onto 3D objects and enhance their visual appearance. By understanding the concept of texture coordinates and their generation, interpolation, wrapping, and manipulation, we can create realistic and visually appealing computer-generated images. Texture mapping is a powerful tool in computer graphics that opens up a world of possibilities for creating immersive and detailed virtual environments. 8.3 Texture Filtering. Texture filtering is an essential technique in computer graphics that aims to improve the visual quality of rendered images by reducing the appearance of aliasing artifacts. Aliasing occurs when the resolution of a texture is lower than the resolution of the screen or when the texture is magnified, resulting in jagged edges and pixelation. Texture filtering helps to smooth out these jagged edges and create a more visually pleasing and realistic representation of the textures. 8.3.1 Introduction to Texture Filtering. Texture filtering is the process of determining the color of a texture element based on its position relative to the pixel being rendered on the screen. It involves sampling multiple texels and interpolating their colors to generate a final color value for the pixel. The goal is to minimize the visual artifacts caused by the discrete nature of textures and to provide a smooth transition between texels. There are several texture filtering techniques available, each with its own advantages and trade-offs. The choice of filtering technique depends on factors such as performance requirements, memory constraints, and the desired visual quality. 8.3.2 Nearest neighbor filtering. Nearest neighbor filtering is the simplest and fastest texture filtering technique. It selects the color of the texel that is closest to the center of the pixel being rendered. This technique is also known as point sampling because it effectively samples a single texel for each pixel. While nearest neighbor filtering is computationally efficient, it can result in noticeable aliasing artifacts, especially when textures are magnified or when there is a significant difference in resolution between the texture and the screen. The lack of interpolation between texels can lead to blocky and pixelated textures. 8.3.3 Bilinear filtering. Bilinear filtering is a more advanced texture filtering technique that provides smoother results compared to nearest neighbor filtering. It works by sampling 4 texels surrounding the center of the pixel and interpolating their colors based on their proximity to the pixel's center. To perform bilinear filtering, the GPU calculates the weighted average of the texel's colors based on their distance from the pixel's center. This interpolation creates a smoother transition between texels and reduces the appearance of aliasing artifacts. Bilinear filtering is widely used in real-time rendering applications due to its balance between visual quality and performance. However, it still has limitations, particularly when textures are significantly magnified or minified, as it can result in blurring or loss of detail. 8.3.4 Trilinear filtering. Trilinear filtering is an extension of bilinear filtering that addresses the issue of texture blurring when textures are minified. When a texture is minified, meaning it is displayed at a smaller size than its original resolution, bilinear filtering alone can result in a loss of detail and a blurry appearance. Trilinear filtering solves this problem by introducing an additional step that blends the colors of 2 map-maps pre-scaled versions of the texture based on the distance between the pixel being rendered and the texture. This blending ensures that the appropriate level of detail is used for each pixel, resulting in a sharper and more accurate representation of the texture. Trilinear filtering is commonly used in applications where textures can be both magnified and minified, such as in 3D games. However, it comes at a higher computational cost compared to bilinear filtering. 8.3.5 Anisotropic filtering. Anisotropic filtering is a more advanced texture filtering technique that provides superior image quality, especially when textures are viewed at oblique angles. It addresses the issue of texture distortion and blurring that can occur when textures are viewed from non-perpendicular angles. Anisotropic filtering works by sampling texels in a pattern that aligns with the direction of the texture's surface. This allows for more accurate sampling and interpolation, resulting in improved texture detail and reduced blurring. While anisotropic filtering offers significant visual improvements, it is also the most computationally expensive texture filtering technique. It requires more memory bandwidth and processing power, making it less suitable for low-end or mobile devices. 8.3.6 Performance considerations. When choosing a texture filtering technique, it is essential to consider the performance implications. More advanced filtering techniques, such as trilinear and anisotropic filtering, require additional computational resources and memory bandwidth compared to simpler techniques like nearest neighbor and bilinear filtering. The performance impact of texture filtering can be mitigated by optimizing the use of MIP maps, which are pre-scaled versions of the texture at different levels of detail. MIP maps can improve both the visual quality and performance by providing the GPU with a smaller set of texels to sample from, depending on the size of the rendered object. Additionally, modern GPUs often provide hardware acceleration for texture filtering, which can significantly improve performance. These hardware features include texture caches, specialized texture units, and dedicated filtering algorithms that offload the filtering computations from the CPU to the GPU. In conclusion, texture filtering is a crucial technique in computer graphics that helps to improve the visual quality of rendered images by reducing aliasing artifacts. Different filtering techniques, such as nearest neighbor, bilinear, trilinear, and anisotropic filtering, offer varying levels of visual quality and performance. Choosing the appropriate texture filtering technique depends on factors such as the desired visual quality, performance requirements, and the capabilities of the target hardware. 8.4 Texture compression. Texture compression is a crucial technique in computer graphics that allows for efficient storage and transmission of texture data. Textures are an essential component of rendering realistic and visually appealing graphics in games, simulations, and other interactive applications. However, textures can consume a significant amount of memory, especially when dealing with high-resolution images or large texture libraries. Texture compression techniques aim to reduce the memory footprint of textures without compromising visual quality. 8.4.1 Introduction to texture compression. Texture compression is the process of reducing the size of texture data while preserving as much visual fidelity as possible. It involves encoding the texture information in a more compact representation, which can be decompressed at runtime to reconstruct the original texture. The goal is to achieve a balance between memory savings and maintaining the visual quality required for the intended application. There are several texture compression formats available, each with its own trade-offs in terms of compression ratio, visual quality, and hardware support. Some of the commonly used texture compression formats include DXT. The DXT, also known as S3TC, compression format is widely supported on graphics hardware and offers a good balance between compression ratio and visual quality. It uses block-based compression, where a 4x4 texel block is compressed into a fixed-size block. DXT compression supports different compression levels, with higher levels providing better quality but requiring more memory. Etc. The etc. Ericsson texture compression format is primarily used in mobile devices and offers a good compression ratio with moderate visual quality. Etc. compression is also block-based, but it uses a different compression algorithm than DXT. Etc. supports both opaque and transparent textures, making it suitable for a wide range of applications. ASTC, the Adaptive Scalable Texture Compression (ASTC) format is a more recent addition to texture compression standards. It provides a wide range of compression options, allowing for better quality and higher compression ratios compared to older formats. ASTC is particularly well suited for high dynamic range (HDR) textures and supports both 2D and 3D textures. 8.4.2 Benefits of texture compression. Texture compression offers several benefits in computer graphics applications. Reduced memory footprint. By compressing textures, the amount of memory required to store them is significantly reduced. This is particularly important in resource-constrained environments such as mobile devices or consoles, where memory usage must be carefully managed. Faster loading times. Compressed textures can be loaded from disk or transmitted over a network more quickly due to their reduced size. This is especially beneficial in real-time applications where textures need to be loaded on the fly during gameplay. Improved performance. Smaller texture sizes result in reduced memory bandwidth requirements, which can lead to improved rendering performance. This is especially true on systems with limited memory bandwidth, such as mobile devices. Increased texture variety. Texture compression allows for a larger variety of textures to be used within the same memory budget. This enables developers to create more visually diverse and detailed environments without exceeding memory limitations. 8.4.3 Texture compression techniques. Texture compression techniques employ various algorithms to reduce the size of texture data. These algorithms take advantage of the inherent redundancy and perceptual limitations of human vision to discard or approximate certain texture details that are less noticeable to the viewer. Some common techniques used in texture compression include block-based compression. This technique divides the texture into fixed-size blocks and compresses each block independently. By exploiting the spatial coherence within a block, block-based compression algorithms can achieve higher compression ratios. DXT and ETC are examples of block-based compression formats. Color quantization. Color quantization reduces the number of unique colors in a texture by approximating similar colors with a smaller palette. This technique is particularly effective for textures with limited color variations, such as normal maps or height maps. Transform coding. Transform coding techniques, such as discrete cosine transform (DCT) or wavelet transform, exploit the frequency characteristics of texture data to achieve compression. These techniques are commonly used in image and video compression algorithms. Error metrics. Texture compression algorithms often use perceptual error metrics to determine the level of detail that can be discarded without significantly impacting visual quality. These metrics take into account the sensitivity of the human visual system to different types of texture artifacts. 8.4.4 Considerations for texture compression. When using texture compression techniques, there are several considerations to keep in mind. Visual quality. While texture compression aims to preserve visual quality, there is always some loss of detail compared to uncompressed textures. It is important to evaluate the visual impact of compression artifacts and ensure they are acceptable for the intended application. Hardware support. Different texture compression formats have varying levels of hardware support across different platforms. It is essential to consider the target hardware and choose a compression format that is widely supported to ensure optimal performance. Compression ratio versus visual quality. Texture compression algorithms offer a range of compression ratios and visual quality trade-offs. It is crucial to find the right balance that meets the memory constraints of the application while maintaining an acceptable level of visual fidelity. Compression time. Depending on the complexity of the compression algorithm and the size of the texture, the compression process can be computationally expensive. It is important to consider the time required for compression, especially when dealing with large texture libraries. In conclusion, texture compression is a vital technique in computer graphics that allows for efficient storage and transmission of texture data. By reducing the memory footprint of textures, texture compression enables developers to create visually appealing graphics while optimizing performance and memory usage. Understanding the different compression formats, techniques, and considerations is crucial for achieving the desired balance between memory savings and visual quality in computer graphics applications. 9. Anti-aliasing techniques. 9.1 Introduction to anti-aliasing. In computer graphics, anti-aliasing is a technique used to reduce the visual artifacts known as jaggies, or aliasing that occur when rendering images with sharp edges or fine details. These artifacts are caused by the discrete nature of digital displays, where pixels are arranged in a grid and can only represent a limited number of colors or shades. Anti-aliasing algorithms work by smoothing out these jagged edges, resulting in a more visually pleasing and realistic image. 9.1.1 What is aliasing? Aliasing occurs when the resolution of an image or object is insufficient to accurately represent its details. This can lead to the appearance of stair-step patterns or jagged edges, especially when rendering high-frequency patterns or diagonal lines. The phenomenon is particularly noticeable in computer graphics, where images are composed of discrete pixels. 9.1.2 The need for anti-aliasing. The human visual system is sensitive to high-frequency changes in luminance and color. When rendering computer-generated images, the discrete nature of pixels can cause abrupt changes in color or intensity along edges, leading to visual artifacts. These artifacts can distract the viewer and reduce the overall quality of the image. Anti-aliasing techniques aim to mitigate these artifacts by introducing subtle variations in color or intensity along the edges, effectively blurring the transition between different colors or shades. This blurring helps to smooth out the jagged edges and create a more natural and visually pleasing appearance. 9.1.3 Types of anti-aliasing techniques. There are several different anti-aliasing techniques used in computer graphics, each with its own strengths and limitations. Some of the commonly used techniques include 9.1.3.1 Supersampling. Supersampling is a brute force approach to anti-aliasing that involves rendering the scene at a higher resolution than the display resolution and then downsampling the result to the target resolution. By sampling multiple points within each pixel, supersampling effectively reduces the visibility of jagged edges. However, this technique can be computationally expensive, as it requires rendering the scene multiple times. 9.1.3.2 Multisampling. Multisampling is a more efficient variation of supersampling that only samples the edges of objects, rather than the entire scene. It works by determining which pixels are covered by a polygon and then samples those pixels at a higher rate. The samples are then combined to produce a final pixel color. Multisampling reduces the computational cost compared to supersampling while still providing good anti-aliasing results. 9.1.3.3 Post-processing anti-aliasing. Post-processing anti-aliasing techniques, such as FXAA, fast approximate anti-aliasing, and SMAA, subpixel morphological anti-aliasing, are applied after the scene has been rendered. These techniques analyze the final image and apply various filters to smooth out the jagged edges. Post-processing anti-aliasing is generally faster than supersampling or multisampling but may not provide the same level of quality. 9.1.4 Performance considerations. Anti-aliasing techniques can have a significant impact on the performance of a computer graphics application. The computational cost of rendering the scene multiple times for supersampling or multisampling can be demanding, especially for real-time applications. Therefore, it is important to consider the performance implications when choosing an anti-aliasing technique. Additionally, the choice of anti-aliasing technique may depend on the specific requirements of the application. For example, real-time applications such as video games may prioritize performance over visual quality, while applications that require high-fidelity rendering, such as architectural visualization or film production, may prioritize visual quality. Conclusion. Anti-aliasing is an essential technique in computer graphics to reduce the visual artifacts caused by aliasing. By smoothing out jagged edges and improving the overall visual quality of rendered images, anti-aliasing techniques enhance the realism and immersion of computer-generated scenes. However, the choice of anti-aliasing technique should consider the trade-off between performance and visual quality, depending on the specific requirements of the application. 9.2 Supersampling. Supersampling is an anti-aliasing technique used in computer graphics to reduce the visual artifacts known as jaggies, or aliasing. It works by rendering the scene at a higher resolution than the display resolution and then downsampling the image to the desired resolution. This process helps to smooth out the jagged edges and improve the overall visual quality of the image. 9.2.1 Introduction to Supersampling. Supersampling, also known as full scene anti-aliasing, FSAA, is a technique that aims to improve the visual quality of computer-generated images by reducing the staircase-like appearance of diagonal lines and curves. It achieves this by sampling multiple points within each pixel and then averaging the color values to produce a final pixel color. By sampling more points, supersampling can capture more detail and produce smoother edges. 9.2.2 Supersampling techniques. There are two main techniques used in supersampling: spatial supersampling and temporal supersampling. 9.2.2.1 Spatial supersampling. Spatial supersampling, also known as traditional supersampling, involves rendering the scene at a higher resolution than the display resolution. This means that each pixel is divided into subpixels, and multiple samples are taken within each subpixel. The color values of these samples are then averaged to determine the final color of the pixel. The higher the number of samples per pixel, the smoother the resulting image will be, but at the cost of increased rendering time. 9.2.2.2 Temporal supersampling. Temporal supersampling, also known as motion blur anti-aliasing, takes advantage of the temporal coherence between consecutive frames to reduce aliasing. Instead of rendering the scene at a higher resolution, temporal supersampling involves rendering multiple frames and then blending them together to create a final image. By incorporating information from previous frames, temporal supersampling can reduce flickering and improve the overall image quality, especially in scenes with moving objects. 9.2.3 Implementation of supersampling. The implementation of supersampling involves modifying the rendering pipeline to support the sampling of multiple points within each pixel. This can be achieved through various techniques, such as 9.2.3.1 Multi-sample anti-aliasing (MSAA). Multi-sample anti-aliasing (MSAA) is a hardware-based technique that is widely supported by modern graphics cards. It involves taking multiple samples within each pixel and storing them in a multi-sample buffer. The color values of these samples are then resolved to a single color value using various techniques, such as alpha to coverage or alpha to 1. MSAA provides a good balance between image quality and performance, as it only requires a moderate increase in rendering time compared to traditional rendering. 9.2.3.2 Super-sampled anti-aliasing (SSAA). Super-sampled anti-aliasing (SSAA) is a software-based technique that involves rendering the scene at a higher resolution and then downsampling the image to the desired display resolution. This technique provides the highest level of anti-aliasing quality but comes at the cost of increased rendering time and memory usage. SSAA is commonly used in offline rendering or in situations where image quality is of utmost importance. 9.2.4 Performance considerations. While supersampling can greatly improve the visual quality of computer-generated images, it comes at a cost in terms of performance. The increased resolution and the need to sample multiple points within each pixel can significantly impact the rendering time and memory usage. Therefore, it is important to consider the performance implications when implementing supersampling. To mitigate the performance impact, various optimizations can be applied, such as adaptive supersampling. Instead of applying supersampling uniformly across the entire scene, adaptive supersampling techniques dynamically adjust the level of supersampling based on the complexity of the scene. This allows for a more efficient allocation of computational resources. GPU acceleration. Graphics processing units (GPUs) are highly parallel processors that excel at performing repetitive tasks, such as rendering multiple samples within each pixel. Utilizing the parallel processing capabilities of GPUs can significantly improve the performance of supersampling techniques. Temporal reprojection. Temporal supersampling techniques can be combined with motion vectors to reproject previous frames onto the current frame. This reduces the number of samples required per pixel and improves performance without sacrificing image quality. Level of detail (LOD) optimization. By adjusting the level of detail based on the distance from the camera, unnecessary supersampling calculations can be avoided for objects that are far away or smaller in size. This helps to optimize performance without compromising visual quality. In conclusion, supersampling is an effective technique for reducing aliasing and improving the visual quality of computer-generated images. By sampling multiple points within each pixel, supersampling can produce smoother edges and more realistic images. However, the increased rendering time and memory usage should be carefully considered, and optimizations should be applied to ensure optimal performance. 9.3 Multisampling. Multisampling is an anti-aliasing technique used in computer graphics to reduce the visual artifacts known as JAGs, or aliasing. It is a method that improves the quality of rendered images by sampling multiple points within each pixel and combining the results to create a smoother appearance. 9.3.1 Introduction to multisampling. Aliasing occurs when the resolution of an image is insufficient to accurately represent a smooth curve or diagonal line. This leads to the appearance of jagged edges, which can be distracting and reduce the overall visual quality of the image. Multisampling addresses this issue by taking multiple samples within each pixel and using them to calculate a final color value. 9.3.2 How multisampling works. In traditional rendering, a single sample is taken at the center of each pixel to determine its color. However, in multisampling, multiple samples are taken at different positions within the pixel. These samples are then used to calculate the final color value for that pixel. During the rendering process, each sample is tested to determine if it falls within the boundaries of the geometry being rendered. If a sample falls within the geometry, its color value is used in the final calculation. If a sample falls outside the geometry, it is discarded. The final color value for each pixel is determined by averaging the color values of all the samples that pass the geometry test. This averaging process helps to smooth out the jagged edges and reduce the appearance of aliasing. 9.3.3 Multisampling techniques. There are several techniques used in multisampling to improve the quality of rendered images. 9.3.3.1 Regular grid sampling. Regular grid sampling is the simplest form of multisampling. It divides each pixel into a regular grid and takes samples at the center of each grid cell. The number of samples taken per pixel can vary, with higher sample counts resulting in better image quality but also increased computational cost. 9.3.3.2 Adaptive sampling. Adaptive sampling is a technique that dynamically adjusts the number of samples taken per pixel based on the complexity of the scene. It focuses more samples on areas with high contrast or fine details, while reducing the number of samples in areas with less detail. This helps to allocate computational resources more efficiently and improve overall performance. 9.3.3.3 Coverage sampling. Coverage sampling is a technique that takes into account the coverage of each sample within a pixel. Instead of simply averaging the color values of all the samples, coverage sampling assigns weights to each sample based on its coverage. Samples with higher coverage contribute more to the final color value, while samples with lower coverage have less influence. This helps to preserve the sharpness of edges while still reducing aliasing. 9.3.4 Implementation of multisampling. Implementing multisampling involves several steps. Enable multisampling in the graphics API or rendering engine being used. Specify the number of samples per pixel. Set up the necessary buffers and resources to store the multiple samples. During the rendering process, take multiple samples within each pixel and perform the necessary tests to determine if they fall within the geometry. Calculate the final color value for each pixel by averaging the color values of the samples that pass the tests. Output the final image with reduced aliasing and improved visual quality. 9.3.5 Performance Considerations. While multisampling can greatly improve the visual quality of rendered images, it does come with some performance considerations. Increased computational cost. Taking multiple samples per pixel requires more processing power and memory bandwidth. Higher sample counts can significantly impact performance. Memory requirements. Storing multiple samples per pixel requires additional memory resources. The amount of memory required increases with the number of samples per pixel. Compatibility. Not all graphics hardware or rendering engines support multisampling. It is important to check the hardware and software requirements before implementing multisampling. To mitigate these performance considerations, it is common to use lower sample counts or employ adaptive sampling techniques to allocate computational resources more efficiently. In conclusion, multisampling is an effective technique for reducing aliasing and improving the visual quality of rendered images. By taking multiple samples within each pixel and combining them, jagged edges are smoothed out, resulting in a more realistic and visually pleasing image. However, it is important to consider the performance implications and compatibility with the hardware and software being used. 9.4 Post-processing anti-aliasing. Post-processing anti-aliasing (PPAA) is a technique used in computer graphics to reduce the visual artifacts known as aliasing that occur when rendering images. Aliasing is the jagged or stair-step appearance of diagonal lines or curved edges in computer-generated images. It is caused by the discrete nature of digital images, where pixels are square and cannot accurately represent smooth curves or diagonal lines. PPAA is applied as a post-processing step after the image has been rendered, making it a popular choice for real-time applications where performance is crucial. It works by analyzing the rendered image and applying various algorithms to smooth out the jagged edges and reduce aliasing artifacts. 9.4.1 Overview of post-processing anti-aliasing techniques. There are several post-processing anti-aliasing techniques available, each with its own strengths and weaknesses. Some of the commonly used techniques include 9.4.1.1 FXAA, Fast Approximate Anti-Aliasing. FXAA is a fast and efficient anti-aliasing technique that works by analyzing the pixel colors in the rendered image and applying a blurring filter to smooth out the jagged edges. It is a relatively simple technique that can be implemented with minimal performance impact. However, FXAA can sometimes blur the image too much, resulting in a loss of detail. 9.4.1.2 SMAA, Subpixel Morphological Anti-Aliasing. SMAA is an advanced anti-aliasing technique that combines both spatial and temporal filtering to reduce aliasing artifacts. It analyzes the pixel colors and patterns in the image to determine the best way to smooth out the edges. SMAA provides high-quality anti-aliasing with minimal blurring, making it a popular choice for many applications. However, SMAA can be computationally expensive and may impact performance. 9.4.1.3 TAA, Temporal Anti-Aliasing. TAA is a technique that takes advantage of the temporal coherence between consecutive frames to reduce aliasing artifacts. It works by blending multiple frames together, using information from previous frames to improve the quality of the current frame. TAA can provide excellent anti-aliasing results, especially in scenes with moving objects or camera motion. However, TAA can introduce motion blur and ghosting artifacts, which may not be desirable in all situations. 9.4.1.4 MLAA, Morphological Anti-Aliasing. MLAA is a technique that uses a combination of edge detection and blurring to reduce aliasing artifacts. It works by identifying edges in the image and applying a blurring filter to smooth out the jagged edges. MLAA can provide good anti-aliasing results with minimal performance impact. However, it may not be as effective in scenes with complex geometry or fine details. 9.4.2 Implementing Post-processing anti-aliasing. Implementing post-processing anti-aliasing techniques involves several steps. First, the rendered image is passed through a pre-processing stage, where any necessary data or buffers are prepared. Then, the anti-aliasing algorithm is applied to the image, either by modifying the pixel colors directly or by applying a post-processing filter. Finally, the resulting image is displayed on the screen or saved to a file. The implementation of post-processing anti-aliasing techniques can vary depending on the chosen algorithm and the graphics framework or engine being used. Most modern graphics APIs provide built-in support for post-processing effects, making it easier to integrate anti-aliasing into the rendering pipeline. 9.4.3 Performance Considerations. When implementing post-processing anti-aliasing, it is important to consider the performance impact on the rendering pipeline. Some anti-aliasing techniques, such as FXAA, have minimal performance impact and can be easily integrated into real-time applications. However, more advanced techniques like SMAA or TAA may require additional computational resources and can impact the overall frame rate. To optimize the performance of post-processing anti-aliasing, several strategies can be employed. One approach is to use lower resolution buffers for the anti-aliasing calculations, reducing the computational cost. Another strategy is to apply anti-aliasing selectively, focusing on areas of the image where aliasing artifacts are most noticeable. Additionally, hardware acceleration techniques, such as using the GPU for parallel processing, can also improve the performance of anti-aliasing algorithms. 9.4.4 Conclusion. Post-processing anti-aliasing is an essential technique in computer graphics to reduce aliasing artifacts and improve the visual quality of rendered images. By applying various algorithms to smooth out jagged edges, post-processing anti-aliasing can significantly enhance the realism and clarity of computer-generated graphics. However, the choice of anti-aliasing technique should be carefully considered, taking into account the performance requirements and visual fidelity of the application. With the right implementation and optimization, post-processing anti-aliasing can greatly enhance the overall visual experience in computer graphics applications. 10. Real-time rendering. 10.1 Introduction to real-time rendering. Real-time rendering is a crucial aspect of computer graphics that focuses on generating and displaying images in real time. Unlike offline rendering, which allows for longer processing times, real-time rendering aims to produce images at interactive frame rates, typically 30 to 60 frames per second. This is essential for applications such as video games, virtual reality, and augmented reality, where responsiveness and smooth visual feedback are paramount. To achieve real-time rendering, various optimization techniques are employed to minimize the computational load and ensure efficient utilization of system resources. Two fundamental techniques used in real-time rendering are frustum culling and occlusion culling. These techniques play a vital role in reducing the number of objects and polygons that need to be processed and rendered, resulting in significant performance improvements. 10.1.1 Frustum culling. Frustum culling is a technique used to determine which objects or parts of objects are visible within the camera's view frustum. The view frustum is a truncated pyramid-shaped volume that represents the portion of the scene visible to the camera. By eliminating objects that are entirely outside the frustum, unnecessary computations and rendering operations can be avoided. The frustum culling process involves several steps. First, the objects in the scene are tested against the frustum's 6 planes to determine if they intersect or lie entirely outside the frustum. Objects that are entirely outside the frustum can be safely discarded, as they are not visible to the camera. Objects that intersect the frustum are further analyzed to determine if they are partially or fully visible. There are several algorithms available for frustum culling, each with its own strengths and weaknesses. Some common algorithms include the bounding sphere test, the bounding box test, and the hierarchical frustum culling. These algorithms vary in complexity and efficiency, and the choice of algorithm depends on the specific requirements of the application. Implementing frustum culling requires maintaining an efficient data structure to store the objects in the scene and perform the necessary intersection tests. Spatial partitioning techniques, such as bounding volume hierarchies, octrees, or quad trees, are often used to organize the scene's objects spatially and facilitate efficient frustum culling. 10.1.2 Occlusion culling. Occlusion culling is another important technique used in real-time rendering to determine which objects or parts of objects are occluded or hidden from view by other objects. Occlusion culling helps reduce the rendering workload by excluding objects that are not visible due to being obstructed by other objects. The occlusion culling process involves identifying occluders, which are objects that can potentially hide other objects, and occludees, which are objects that can be hidden or occluded. The visibility of occludees is determined by testing if they are occluded by occluders. If an occludee is fully occluded, it can be safely excluded from the rendering process. There are various techniques available for occlusion culling, including the depth buffer method, the occlusion query method, and the occlusion mesh method. The depth buffer method utilizes the depth buffer, a per-pixel buffer that stores the depth information of the scene, to determine occlusion. The occlusion query method uses GPU queries to determine if an object is visible or occluded. The occlusion mesh method involves creating simplified occlusion meshes that approximate the occluder's shapes and perform occlusion tests against them. Implementing occlusion culling requires careful consideration of the scene's complexity and the available system resources. The choice of occlusion culling technique depends on factors such as the scene's geometry, the number of occluders and occludees, and the desired level of accuracy. 10.1.3 Performance considerations. While frustum culling and occlusion culling can significantly improve rendering performance, they also introduce additional computational overhead. The cost of performing culling operations must be balanced with the potential performance gains achieved by reducing the number of objects to be processed and rendered. The efficiency of frustum culling and occlusion culling depends on several factors, including the complexity of the scene, the number of objects, the culling algorithms used, and the hardware capabilities of the system. It is essential to profile and optimize the culling process to achieve the best possible performance. Furthermore, the effectiveness of frustum culling and occlusion culling can be influenced by dynamic objects and scenes with frequent changes. In such cases, the culling process needs to be updated dynamically to account for object movement and changes in occlusion relationships. In conclusion, frustum culling and occlusion culling are vital techniques in real-time rendering that help optimize performance by reducing the number of objects and polygons that need to be processed and rendered. By efficiently determining visible objects and occluded areas, these techniques contribute to achieving interactive frame rates and enhancing the overall user experience in applications such as video games and virtual reality. 10.2 Real-time rendering techniques. Real-time rendering is a crucial aspect of computer graphics, especially in interactive applications such as video games and virtual reality. It involves generating and displaying images in real time, typically at a high frame rate, to provide a smooth and immersive visual experience to the user. In this section, we will explore some of the key techniques used in real-time rendering. 10.2.1 Frustum culling. Frustum culling is a technique used to optimize rendering by eliminating objects that are outside the view frustum, which is the portion of the scene visible to the camera. By discarding objects that are not visible, we can significantly reduce the number of objects that need to be processed and rendered, resulting in improved performance. The frustum is defined by 6 planes: near, far, left, right, top, and bottom. Any object completely outside the frustum can be safely culled, as it will not contribute to the final image. To determine if an object is inside or outside the frustum, we can perform a simple test using the object's bounding volume, such as a bounding box or bounding sphere. There are various algorithms available for frustum culling, each with its own trade-offs in terms of complexity and accuracy. Some common algorithms include the view frustum culling algorithm, which checks if the object's bounding volume intersects with any of the frustum planes, and the occlusion culling algorithm, which takes into account occlusion from other objects. 10.2.2 Occlusion culling. Occlusion culling is a technique used to further optimize rendering by eliminating objects that are occluded or hidden from view by other objects. It takes into account the occlusion relationship between objects to determine which objects are visible and which can be safely culled. One approach to occlusion culling is the use of occlusion queries, which involve rendering a simplified version of the scene to determine which objects are visible. This is done by rendering the scene from the camera's viewpoint, but with depth testing disabled. Each object is rendered with a unique color, and the resulting image is read back from the GPU. By comparing the colors of the objects in the image, we can determine which objects are visible and which are occluded. Another approach to occlusion culling is the use of occlusion meshes or occlusion volumes. These are simplified representations of the scene geometry that are used to approximate the occlusion relationship between objects. By testing the visibility of these occlusion meshes or volumes, we can determine which objects are occluded and can be culled. 10.2.3 Performance considerations. While frustum culling and occlusion culling can greatly improve rendering performance, they also introduce additional overhead. The cost of performing culling tests and managing the culling data structures must be balanced against the potential performance gains. One important consideration is the complexity of the scene and the number of objects that need to be culled. As the scene becomes more complex and the number of objects increases, the cost of culling tests also increases. Therefore, it is important to carefully optimize the culling algorithms and data structures to minimize the overhead. Another consideration is the dynamic nature of the scene. If the scene is constantly changing, with objects moving in and out of the view frustum or occluding each other, the culling data structures need to be updated frequently. This can introduce additional overhead and may require more sophisticated culling algorithms to handle the dynamic nature of the scene. It is also important to consider the hardware capabilities of the target platform. Different platforms have different levels of support for culling techniques, and some techniques may be more suitable for certain hardware architectures. Therefore, it is important to profile and optimize the culling techniques for the target platform to achieve the best performance. In conclusion, frustum culling and occlusion culling are essential techniques in real-time rendering to optimize performance by eliminating objects that are outside the view frustum or occluded by other objects. However, careful consideration must be given to the complexity of the scene, the dynamic nature of the scene, and the hardware capabilities to achieve the best performance. 10.3 Performance optimization in real-time rendering. Real-time rendering is a crucial aspect of computer graphics, especially in applications such as video games and virtual reality. To achieve smooth and immersive experiences, it is essential to optimize the performance of real-time rendering techniques. This section will explore various performance optimization strategies that can be employed in real-time rendering. 10.3.1 Frustum culling. Frustum culling is a technique used to eliminate objects that are outside the view frustum, which is the portion of the scene visible to the camera. By removing these objects from the rendering process, significant performance gains can be achieved. 10.3.1.1 Overview of frustum culling. The view frustum is defined by 6 planes that form a pyramid-like shape with the camera as the apex. Any object completely outside the frustum does not need to be rendered, as it will not be visible on the screen. Frustum culling involves testing each object's bounding volume against these frustum planes to determine if it is inside or outside the view frustum. 10.3.1.2 Frustum culling algorithms. There are several algorithms available for frustum culling, each with its own advantages and limitations. Some commonly used algorithms include Axis-aligned bounding box AABB test. This algorithm uses the object's axis-aligned bounding box to quickly determine if it intersects with the frustum. It is a simple and efficient method but may result in false positives for objects with irregular shapes. Sphere test. In this algorithm, each object is approximated by a bounding sphere. The sphere is tested against the frustum planes to determine if it intersects or lies completely outside the frustum. This method provides a more accurate culling result than the AABB test but requires additional computations. View frustum culling. This algorithm involves transforming the object's bounding volume into view space and testing it against the frustum planes. It provides accurate culling results but requires more computational resources. 10.3.1.3 Implementation of frustum culling. To implement frustum culling, the first step is to calculate the view frustum planes based on the camera's position and orientation. Once the frustum planes are defined, each object's bounding volume is tested against these planes to determine its visibility. The implementation of frustum culling can be done on the CPU or the GPU. On the CPU, the culling calculations are performed for each object in the scene, and the results are used to determine which objects should be sent to the GPU for rendering. On the GPU, the culling calculations can be performed using compute shaders or geometry shaders, which can significantly improve performance by parallelizing the culling process. 10.3.1.4 Performance considerations. Frustum culling can provide substantial performance improvements by reducing the number of objects that need to be processed and rendered. However, it is important to consider the trade-off between culling accuracy and computational cost. More accurate culling methods may require additional computations, which can impact overall performance. Additionally, the efficiency of frustum culling depends on the complexity of the scene and the distribution of objects. If the scene contains a large number of small objects or objects that are densely packed, the culling calculations may become more computationally expensive. 10.3.2 Occlusion culling. Occlusion culling is another technique used to optimize real-time rendering by eliminating objects that are occluded or hidden from view. By identifying and removing these occluded objects, the rendering workload can be significantly reduced, resulting in improved performance. 10.3.2.1 Overview of occlusion culling. Occlusion culling involves determining which objects are not visible due to being occluded by other objects in the scene. This can be achieved by performing visibility tests between objects or by utilizing occlusion queries. 10.3.2.2 Occlusion culling techniques. There are several occlusion culling techniques available, each with its own strengths and weaknesses. Some commonly used techniques include view frustum culling. Similar to frustum culling, this technique involves testing each object's bounding volume against the view frustum. If an object is completely outside the frustum, it is considered occluded and can be culled. Portal culling. This technique is based on the concept of portals, which are openings between different areas of a scene. By determining which portals are visible from the current viewpoint, objects that are not visible through any open portals can be culled. Hierarchical occlusion maps. This technique involves pre-computing occlusion information for the scene and storing it in a hierarchical data structure. During rendering, the occlusion information is used to quickly determine which objects are occluded and can be culled. 10.3.2.3 Implementation of occlusion culling. The implementation of occlusion culling can be done on the CPU or the GPU. On the CPU, occlusion culling calculations are performed for each object in the scene to determine its visibility. On the GPU, occlusion culling can be implemented using occlusion queries, which allow the GPU to determine if an object is visible or occluded. 10.3.2.4 Performance considerations. Occlusion culling can provide significant performance improvements by reducing the rendering workload. However, it is important to consider the trade-off between culling accuracy and computational cost. More accurate occlusion culling methods may require additional computations, which can impact overall performance. The efficiency of occlusion culling also depends on the complexity of the scene and the distribution of occluders. If the scene contains a large number of occluders or occluders that are densely packed, the occlusion culling calculations may become more computationally expensive. In conclusion, frustum culling and occlusion culling are essential techniques for optimizing real-time rendering performance. By eliminating objects that are outside the view frustum or occluded from view, these techniques can significantly reduce the rendering workload and improve overall performance. However, it is important to carefully consider the trade-offs between culling accuracy and computational cost to achieve the desired balance between performance and visual quality. 10.4 GPU Programming for real-time rendering. In real-time rendering, the graphics processing unit (GPU) plays a crucial role in achieving high-performance graphics. The GPU is responsible for executing the rendering pipeline and performing various computations required for rendering scenes in real time. To fully utilize the power of the GPU, developers need to understand how to program it efficiently. This section will explore the fundamentals of GPU programming for real-time rendering, focusing on techniques such as frustum culling and occlusion culling. 10.4.1 Introduction to GPU Programming. GPU programming involves writing code that runs on the GPU to perform parallel computations. Unlike traditional CPU programming, where instructions are executed sequentially, GPU programming takes advantage of the massive parallelism offered by the GPU's architecture. This parallelism allows for the efficient processing of large amounts of data simultaneously. Modern GPUs are designed with specialized hardware components, such as vertex shaders, pixel shaders, and geometry shaders, which can be programmed using shading languages like OpenGL Shading Language (GLSL) or High-Level Shading Language (HLSL). These shaders enable developers to control various stages of the rendering pipeline and perform computations on individual vertices and fragments. 10.4.2 Frustum culling on the GPU. Frustum culling is a technique used to eliminate objects that are outside the view frustum, which is the portion of the scene visible to the camera. By discarding objects that are not visible, frustum culling reduces the number of objects that need to be processed, resulting in significant performance improvements. Implementing frustum culling on the GPU involves passing the view frustum's parameters to the shader program and performing intersection tests between the frustum and the bounding volumes of objects. The shader program can then discard fragments or vertices that are outside the frustum, preventing unnecessary computations for invisible objects. To efficiently perform frustum culling on the GPU, developers can utilize techniques like hierarchical frustum culling, where the scene is organized into a spatial hierarchy, such as an octree or a bounding volume hierarchy. This allows for early termination of the culling process when entire branches of the hierarchy are determined to be outside the frustum. 10.4.3 Occlusion culling on the GPU. Occlusion culling is a technique used to determine which objects are occluded or hidden from view by other objects in the scene. By identifying occluded objects, occlusion culling reduces the number of objects that need to be rendered, resulting in improved performance. Implementing occlusion culling on the GPU involves using occlusion queries, which are GPU commands that determine the number of fragments or pixels that pass the depth test. By rendering occluders into the depth buffer and querying the number of fragments that pass the depth test, occluded objects can be identified and skipped during rendering. To efficiently perform occlusion culling on the GPU, developers can utilize techniques like hierarchical occlusion culling, where the scene is organized into a spatial hierarchy similar to frustum culling. This allows for early termination of the occlusion culling process when entire branches of the hierarchy are determined to be occluded. 10.4.4 Performance considerations in GPU programming. When programming the GPU for real-time rendering, several performance considerations should be taken into account to maximize efficiency. 10.4.4.1 Batch rendering. Batch rendering involves grouping similar objects together and rendering them in a single draw call. This reduces the overhead of state changes and draw calls, resulting in improved performance. By minimizing the number of draw calls, developers can achieve better GPU utilization and reduce CPU-GPU communication overhead. 10.4.4.2 Data locality. To optimize memory access on the GPU, it is essential to ensure data locality. This means organizing data in a way that minimizes memory access latency and maximizes cache utilization. By accessing memory coherently and minimizing memory transfers, developers can improve the overall performance of GPU programs. 10.4.4.3 GPU memory management. Efficient GPU memory management is crucial for real-time rendering. Developers should minimize memory allocations and deallocations during runtime to avoid performance penalties. Techniques like object pooling and reusing memory buffers can help reduce memory fragmentation and improve GPU memory utilization. 10.4.4.4 Shader optimization. Optimizing shaders is essential for achieving real-time rendering performance. This involves minimizing the number of instructions, reducing memory access, and utilizing GPU-specific features efficiently. Techniques like loop unrolling, register allocation, and texture compression can significantly improve shader performance. Conclusion. GPU programming is a fundamental aspect of real-time rendering, enabling developers to harness the power of modern GPUs for high-performance graphics. Techniques like frustum culling and occlusion culling can be efficiently implemented on the GPU, reducing the computational load and improving rendering performance. By considering performance considerations and optimizing GPU programs, developers can achieve real-time rendering with smooth and immersive graphics. 11. Virtual reality and augmented reality. 11.1 Introduction to virtual reality and augmented reality. Virtual reality (VR) and augmented reality (AR) are two rapidly evolving technologies that have revolutionized the way we interact with digital content. Both VR and AR provide immersive experiences by blending the virtual world with the real world, but they differ in their approach and application. 11.1.1 Virtual reality. Virtual reality refers to a simulated environment that can be similar to or completely different from the real world. It typically involves the use of a head-mounted display (HMD) that covers the user's eyes and displays a virtual environment. VR also often incorporates other sensory inputs such as audio and haptic feedback to enhance the immersive experience. The goal of VR is to transport the user into a completely virtual world, where they can interact with objects and environments that do not exist in reality. This technology has found applications in various fields, including gaming, education, training, and simulation. In VR, the user's physical surroundings are completely replaced by the virtual environment, creating a sense of presence and immersion. 11.1.2 Augmented reality. Augmented reality, on the other hand, overlays digital content onto the real world, enhancing the user's perception and interaction with their surroundings. AR technology typically involves the use of a transparent display, such as a smartphone or smart glasses, through which the user can see both the real world and the virtual content. AR enhances the user's perception of reality by adding virtual objects, information, or graphics to their real-world environment. This technology has gained popularity in various industries, including gaming, navigation, marketing, and industrial applications. Unlike VR, AR does not replace the real world but augments it with additional digital information. 11.1.3 Rendering for virtual reality. Rendering for virtual reality presents unique challenges due to the need for high frame rates and low latency to maintain a smooth and immersive experience. To achieve this, several optimization techniques are employed in the rendering pipeline. 11.1.3.1 Frustum culling in VR. Frustum culling is a technique used to eliminate objects that are outside the user's field of view, reducing the number of objects that need to be rendered. In VR, where the user's head movements determine the view, frustum culling becomes even more critical to maintain high performance. By using the concept of the frustum, which is the portion of the viewing volume that is visible to the user, objects outside this frustum can be culled from the rendering process. This optimization technique helps to reduce the number of unnecessary calculations and improves the overall performance of the VR application. 11.1.3.2 Occlusion culling in VR. Occlusion culling is another important technique in VR rendering that helps to improve performance by eliminating objects that are occluded or hidden from the user's view. In VR, where the user can move around and interact with the virtual environment, occlusion culling becomes crucial to maintain a realistic and immersive experience. By analyzing the visibility of objects from the user's perspective, occlusion culling algorithms can determine which objects are not visible and can be culled from the rendering process. This optimization technique reduces the computational load and improves the rendering performance in VR applications. 11.1.4 Rendering for augmented reality. Rendering for augmented reality also presents unique challenges, as the virtual content needs to be seamlessly integrated with the real-world environment. To achieve this, various optimization techniques are employed in the rendering pipeline. 11.1.4.1 Frustum culling in AR. Frustum culling is equally important in AR rendering as it helps to eliminate objects that are outside the user's field of view. By using the concept of the frustum, objects that are not visible to the user can be culled, reducing the rendering workload and improving the overall performance of the AR application. 11.1.4.2 Occlusion culling in AR. Occlusion culling is also crucial in AR rendering to ensure that virtual objects are correctly occluded by real-world objects. By analyzing the depth and visibility of objects in the real-world environment, occlusion culling algorithms can determine which virtual objects should be hidden or partially visible, creating a more realistic and immersive AR experience. 11.1.5 Performance considerations in VR and AR. Both VR and AR applications require high-performance rendering to maintain a smooth and immersive experience. To achieve this, several performance considerations need to be taken into account. 11.1.5.1 Frame rate and latency. In VR and AR, maintaining a high frame rate is crucial to avoid motion sickness and provide a comfortable experience. A frame rate of at least 60 frames per second (FPS) is generally recommended to achieve smooth visuals. Additionally, low latency is essential to minimize the delay between the user's movements and the corresponding changes in the virtual or augmented environment. 11.1.5.2 Optimization techniques. Various optimization techniques, such as frustum culling, occlusion culling, and level of detail (LOD) rendering, are employed to reduce the computational load and improve rendering performance in VR and AR applications. These techniques help to minimize the number of unnecessary calculations and ensure that only the visible and relevant objects are rendered. 11.1.5.3 Hardware considerations. The hardware used for VR and AR applications plays a significant role in determining the overall performance. High-performance graphics processing units (GPUs), fast processors, and sufficient memory are essential to handle the computational demands of rendering complex virtual or augmented environments. In conclusion, virtual reality and augmented reality have transformed the way we interact with digital content. Rendering for VR and AR requires specialized optimization techniques, such as frustum culling and occlusion culling, to maintain high performance and provide a seamless and immersive experience. Performance considerations, including frame rate, latency, and hardware capabilities, are crucial in ensuring a smooth and realistic VR or AR experience. 11.2 Rendering for virtual reality. Virtual reality (VR) is an immersive technology that allows users to experience a computer-generated environment as if they were physically present in it. The success of VR heavily relies on the ability to render realistic and high-quality graphics in real time. In this section, we will explore the unique challenges and considerations involved in rendering for virtual reality. 11.2.1 Stereoscopic rendering. One of the fundamental aspects of VR rendering is the creation of a stereoscopic effect, which provides depth perception by presenting slightly different images to each eye. This technique mimics the way our eyes perceive the world and enhances the sense of immersion. To achieve stereoscopic rendering, the scene is rendered from two slightly different viewpoints, corresponding to the left and right eye positions. These two images are then combined and displayed to the user through a VR headset. Stereoscopic rendering introduces additional computational overhead since the scene needs to be rendered twice. To optimize performance, various techniques can be employed. One common approach is to use multi-threading or parallel processing to distribute the rendering workload across multiple CPU cores or GPU threads. This allows for efficient utilization of hardware resources and reduces the overall rendering time. 11.2.2 Field of view. In virtual reality, the field of view (FOV) plays a crucial role in creating a convincing and immersive experience. The FOV determines the extent of the virtual world that is visible to the user at any given time. To achieve a sense of presence, the FOV should closely match the natural human field of view, which is approximately 180 degrees. Rendering a wide FOV can be demanding in terms of computational resources. The larger the FOV, the more objects and geometry need to be rendered, resulting in increased processing requirements. To optimize performance, developers often employ techniques such as frustum culling and occlusion culling, which selectively render only the objects that are within the user's view frustum or are not occluded by other objects. 11.2.3 Motion to photon latency. Motion to photon latency refers to the delay between the user's head movement and the corresponding update of the displayed image in the VR headset. Minimizing this latency is crucial for providing a smooth and comfortable VR experience. High latency can lead to motion sickness and a sense of disconnection between the user's movements and the virtual environment. To reduce motion to photon latency, several optimization techniques can be employed. One approach is to utilize predictive tracking algorithms that estimate the user's head movement and render the next frame in advance. This helps to minimize the delay between the user's movement and the updated display. Additionally, using high refresh rate displays and reducing the rendering workload through techniques like level of detail (LOD) can also contribute to reducing latency. 11.2.4 Resolution and image quality. Achieving high resolution and high quality visuals is essential for creating a realistic and immersive VR experience. However, rendering at high resolutions can be computationally expensive and may strain the hardware capabilities of VR systems. Balancing performance and image quality is crucial to ensure a smooth and responsive VR experience. To optimize rendering for VR, developers often employ techniques such as dynamic resolution scaling. This technique adjusts the rendering resolution based on the performance capabilities of the VR system. During demanding scenes, the resolution can be dynamically reduced to maintain a consistent frame rate. Conversely, during less demanding scenes, the resolution can be increased to enhance image quality. Furthermore, techniques like anti-aliasing and texture filtering can be used to improve the visual quality of the rendered images. These techniques help to reduce jagged edges and enhance the clarity of textures, resulting in a more visually appealing VR experience. 11.2.5 Interaction and user interface. In addition to rendering the virtual environment, VR applications often require rendering interactive elements and user interfaces. These elements can include menus, buttons, and other graphical overlays that allow users to interact with the virtual world. Rendering these elements efficiently and ensuring their responsiveness is crucial for a seamless user experience. To optimize the rendering of interactive elements, developers often utilize techniques such as GPU instancing and batching. GPU instancing allows for the efficient rendering of multiple instances of the same object, reducing the number of draw calls and improving performance. Batching involves combining multiple objects into a single mesh or texture, further reducing the rendering overhead. Additionally, developers need to consider the user interface's depth and position within the 3D space. Properly aligning the user interface with the user's field of view and ensuring it remains visible and legible during head movements is essential for a comfortable and intuitive VR experience. In conclusion, rendering for virtual reality presents unique challenges and considerations compared to traditional computer graphics. Stereoscopic rendering, field of view optimization, motion to photon latency reduction, resolution and image quality optimization, and efficient rendering of interactive elements are all crucial aspects of creating a compelling and immersive VR experience. By employing various optimization techniques and leveraging the capabilities of modern hardware, developers can deliver visually stunning and responsive VR applications. 11.3 Rendering for augmented reality. Augmented reality (AR) is a technology that combines the real world with virtual elements, enhancing the user's perception and interaction with their environment. In AR, the challenge lies in seamlessly integrating virtual objects into the real world, making them appear as if they exist in the same space. Rendering for augmented reality involves several techniques, including frustum culling and occlusion culling, to optimize the rendering process and ensure a smooth and realistic AR experience. 11.3.1 Frustum culling in augmented reality. Frustum culling is a technique used to determine which objects in a scene are visible within the camera's view frustum. In AR, the camera represents the user's viewpoint, and the view frustum defines the portion of the scene that is visible to the user. By performing frustum culling, we can eliminate objects that are outside the view frustum, reducing the number of objects that need to be rendered and improving performance. In AR applications, frustum culling is crucial for maintaining a high frame rate and providing a responsive user experience. Since AR often involves real-time interaction and tracking of virtual objects, it is essential to optimize the rendering process to ensure smooth and accurate alignment of virtual objects with the real world. To implement frustum culling in AR, we need to calculate the view frustum based on the camera's position, orientation, and field of view. This can be done using projection matrices and the camera's intrinsic and extrinsic parameters. Once the view frustum is defined, we can perform frustum culling by checking each object's bounding volume against the frustum. Objects that are completely outside the frustum can be safely culled, while objects partially or fully inside the frustum need to be rendered. It is important to note that in AR, the view frustum may change dynamically as the user moves or interacts with the virtual objects. Therefore, frustum culling needs to be performed continuously to adapt to these changes and ensure that only the visible objects are rendered. 11.3.2 Occlusion culling in augmented reality. Occlusion culling is another important technique in AR rendering that helps optimize the rendering process by identifying and eliminating objects that are occluded or hidden from the camera's view. Occlusion occurs when a virtual object is obstructed by real-world objects or other virtual objects, making it unnecessary to render the occluded parts. In AR, occlusion culling is crucial for creating a realistic and immersive experience. By accurately determining which parts of virtual objects are visible and which are occluded, we can ensure that virtual objects interact seamlessly with the real world, appearing to be behind or in front of real-world objects as expected. To implement occlusion culling in AR, we need to consider the geometry and depth information of both the real-world environment and the virtual objects. Techniques such as depth buffering, depth testing, and depth peeling can be used to determine the visibility of objects and their occluded parts. By comparing the depth values of pixels in the scene, we can identify occluded areas and exclude them from the rendering process. In addition to depth-based occlusion culling, other techniques such as hierarchical occlusion maps and occlusion queries can also be employed in AR rendering. These techniques involve pre-computing occlusion information or using GPU queries to determine the visibility of objects, further optimizing the rendering process and improving performance. It is worth mentioning that occlusion culling in AR can be challenging due to the dynamic nature of the real-world environment. Objects and occlusion relationships may change as the user moves or interacts with the scene. Therefore, occlusion culling needs to be performed continuously and efficiently to adapt to these changes and provide a seamless AR experience. 11.3.3 Performance considerations in AR rendering. Rendering for augmented reality poses unique performance challenges due to the real-time nature of AR applications and the need for seamless integration of virtual objects with the real world. To ensure a smooth and responsive AR experience, several performance considerations should be taken into account. Optimized rendering pipeline. AR applications often require real-time rendering of complex scenes. Optimizing the rendering pipeline by minimizing redundant calculations, reducing overdraw, and utilizing efficient rendering techniques can significantly improve performance. Level of detail (LOD). Implementing LOD techniques can help manage the complexity of virtual objects based on their distance from the camera. By rendering simplified versions of objects when they are far away, we can reduce the number of polygons and texture data processed, improving performance without sacrificing visual quality. Dynamic occlusion culling. As mentioned earlier, occlusion culling is crucial in AR rendering. However, the dynamic nature of AR environments requires continuous and efficient occlusion culling algorithms to adapt to changes in the scene and maintain a high frame rate. Hardware acceleration. Utilizing hardware acceleration features, such as GPU programming and specialized AR hardware, can significantly improve rendering performance. Taking advantage of features like parallel processing, texture compression, and shader optimization can help achieve real-time rendering in AR applications. Scene optimization. Optimizing the scene by reducing the number of objects, simplifying geometry, and using efficient data structures can improve rendering performance. Techniques like spatial partitioning, such as octrees or quad trees, can help organize the scene and speed up visibility calculations. Real-time tracking. AR applications often rely on real-time tracking of the user's position and orientation. Efficient tracking algorithms and hardware integration can minimize latency and ensure accurate alignment of virtual objects with the real world. By considering these performance considerations and implementing efficient rendering techniques, developers can create AR applications that deliver a seamless and immersive experience to users. Optimizing the rendering process in AR is crucial for achieving high frame rates, reducing latency, and providing a realistic integration of virtual objects into the real world. 11.4 Performance considerations in VR and AR. Virtual reality (VR) and augmented reality (AR) have gained significant popularity in recent years, offering immersive and interactive experiences to users. However, the seamless integration of virtual and real-world elements in real-time poses unique challenges in terms of performance. In this section, we will explore the performance considerations in VR and AR, focusing on frustum culling and occlusion culling techniques. 11.4.1 Frustum culling in VR and AR. Frustum culling is a technique used to determine which objects in a scene are visible within the camera's view frustum. In VR and AR applications, where the user's viewpoint can change dynamically, frustum culling becomes even more critical to maintain a high frame rate and ensure a smooth user experience. Dynamic frustum culling. In VR and AR, the camera's frustum needs to be updated continuously as the user moves their head or changes their perspective. This requires dynamically recalculating the frustum and performing frustum culling on the scene objects. The efficiency of the frustum culling algorithm becomes crucial to avoid unnecessary computations and improve overall performance. Hierarchical frustum culling. Hierarchical frustum culling is a technique that divides the scene into a hierarchy of bounding volumes, such as octrees or bounding volume hierarchies. This approach allows for efficient culling by quickly discarding entire groups of objects that are outside the frustum. In VR and AR, where the scene complexity can be high, hierarchical frustum culling can significantly reduce the number of objects that need to be rendered, resulting in improved performance. Occlusion culling in VR and AR. Occlusion culling is another important technique in VR and AR applications, aimed at reducing the rendering workload by eliminating objects that are not visible due to being occluded by other objects. Occlusion culling becomes particularly crucial in scenarios where the user interacts with virtual objects in the real world, as occluded objects can cause visual inconsistencies and reduce the sense of immersion. 11.4.2 Occlusion culling techniques. Various occlusion culling techniques can be employed in VR and AR applications to improve performance and enhance the visual quality of the rendered scene. View frustum culling. Similar to frustum culling, view frustum culling is used to determine which objects are visible within the camera's view frustum. By discarding objects that are outside the frustum, unnecessary computations and rendering can be avoided, resulting in improved performance. Portal culling. Portal culling is a technique commonly used in indoor VR and AR environments. It involves dividing the scene into interconnected rooms or areas and using portals to determine visibility between them. By culling objects that are not visible through portals, the rendering workload can be significantly reduced. Conservative visibility culling. Conservative visibility culling is a technique that aims to eliminate overdraw by culling objects that are not visible due to being completely occluded by other objects. This technique involves using conservative bounding volumes, such as axis-aligned bounding boxes, to approximate the visibility of objects. By accurately determining occlusion, unnecessary rendering can be avoided, resulting in improved performance. 11.4.3 Performance considerations in VR and AR. In VR and AR applications, maintaining a high frame rate is crucial to provide a smooth and immersive experience to the user. However, the performance requirements are more demanding compared to traditional computer graphics applications due to the real-time nature and the need for seamless integration of virtual and real-world elements. Here are some key performance considerations in VR and AR. Frame rate. Achieving and maintaining a high frame rate is essential in VR and AR applications to avoid motion sickness and provide a comfortable experience to the user. The frame rate should ideally be 90 frames per second (FPS) or higher to ensure smooth and responsive visuals. Performance optimization techniques, such as frustum culling and occlusion culling, play a vital role in achieving the desired frame rate. Latency. Reducing latency is critical in VR and AR applications to minimize the delay between the user's actions and the corresponding visual feedback. High latency can lead to a disconnect between the user's movements and the virtual environment, resulting in a less immersive experience. Optimizing rendering techniques, such as frustum culling and occlusion culling, can help reduce latency by minimizing unnecessary computations and rendering. Rendering quality. Maintaining a balance between rendering quality and performance is crucial in VR and AR applications. While high-quality visuals enhance the sense of immersion, they can also put a significant strain on the system's resources. Performance optimization techniques, such as level of detail (LOD) and texture compression, can be employed to dynamically adjust the rendering quality based on the user's viewpoint and the available resources. Hardware considerations. The hardware used in VR and AR systems plays a vital role in determining the overall performance. High-performance graphics processing units (GPUs), fast processors, and sufficient memory are essential to handle the computational demands of rendering complex scenes in real time. Additionally, optimizing GPU programming techniques specific to VR and AR can further enhance performance. In conclusion, performance considerations in VR and AR applications are crucial to provide a seamless and immersive experience to the user. Techniques such as frustum culling and occlusion culling play a significant role in optimizing rendering performance, reducing latency, and maintaining a high frame rate. By carefully considering these performance considerations and employing appropriate optimization techniques, developers can create compelling VR and AR experiences that push the boundaries of computer graphics. 12. Future trends in computer graphics. 12.1 Advancements in graphics hardware. Advancements in graphics hardware have played a crucial role in the evolution of computer graphics. Over the years, there have been significant improvements in the capabilities and performance of graphics processing units, GPUs, which have revolutionized the field of computer graphics. These advancements have enabled the development of more realistic and immersive virtual environments, as well as the efficient rendering of complex scenes in real time. 12.1.1 Evolution of graphics processing units, GPUs. Graphics processing units have come a long way since their inception. Initially, GPUs were primarily designed to handle basic 2D rendering tasks, such as displaying windows and icons on a computer screen. However, with the increasing demand for more realistic and visually appealing graphics, GPUs have evolved into highly specialized processors capable of performing complex calculations required for 3D rendering. The early GPUs were fixed-function units, meaning they were designed to perform specific tasks, such as transforming vertices and rasterizing polygons. These GPUs had limited programmability and were not capable of handling advanced rendering techniques efficiently. However, with the introduction of programmable shaders, GPUs became more flexible and versatile. Modern GPUs are highly parallel processors, consisting of thousands of cores that can execute multiple instructions simultaneously. This parallel architecture allows GPUs to process large amounts of data in parallel, making them ideal for computationally intensive tasks like rendering complex scenes. Additionally, GPUs now support advanced shading models, texture mapping, and other rendering techniques, enabling the creation of more realistic and visually stunning graphics. 12.1.2 Frustum culling and occlusion culling on GPUs. Frustum culling and occlusion culling are two optimization techniques commonly used in computer graphics to improve rendering performance. These techniques aim to reduce the number of objects that need to be rendered by identifying and eliminating objects that are not visible or occluded from the camera's view. With advancements in graphics hardware, GPUs have become more efficient at performing frustum culling and occlusion culling. The parallel processing capabilities of GPUs allow for the simultaneous testing of multiple objects against the view frustum or occlusion queries. This parallelism significantly speeds up the culling process, resulting in improved rendering performance. Modern GPUs also provide dedicated hardware support for occlusion culling techniques such as hierarchical occlusion maps and occlusion queries. These hardware-accelerated techniques enable the GPU to quickly determine whether an object is occluded by other objects in the scene, allowing for more accurate culling decisions. Furthermore, GPUs now support advanced culling algorithms, such as conservative rasterization and tile-based rendering, which further optimize the culling process. Conservative rasterization ensures that only visible pixels are processed, reducing unnecessary computations. Tile-based rendering divides the screen into smaller tiles and performs culling on a per-tile basis, minimizing the amount of work required for culling. 12.1.3 Performance improvements in rendering. Advancements in graphics hardware have led to significant performance improvements in rendering complex scenes. The increased computational power of modern GPUs allows for the rendering of larger and more detailed environments with higher frame rates. One of the key advancements in graphics hardware is the introduction of hardware-accelerated ray tracing. Ray tracing is a rendering technique that simulates the behavior of light in a scene, resulting in more realistic lighting and reflections. Traditionally, ray tracing was computationally expensive and not feasible for real-time rendering. However, with the introduction of dedicated ray tracing hardware in GPUs, real-time ray tracing has become a reality, enabling more accurate and visually stunning graphics. Another area of improvement is in the rendering of dynamic scenes. GPUs now support techniques such as instancing and hardware-based skinning, which optimize the rendering of multiple instances of the same object or characters with complex animations. These techniques reduce the amount of data that needs to be processed, resulting in improved rendering performance. Furthermore, advancements in graphics hardware have also led to improvements in texture mapping and anti-aliasing techniques. GPUs now support more advanced texture filtering algorithms, such as anisotropic filtering and MIP mapping, which enhance the visual quality of textures. Anti-aliasing techniques, which reduce jagged edges and improve image quality, have also benefited from the increased computational power of GPUs, allowing for more efficient and higher quality anti-aliasing algorithms. 12.1.4 Future trends in graphics hardware. The advancements in graphics hardware are expected to continue in the future, further pushing the boundaries of computer graphics. Some of the future trends in graphics hardware include 12.1.4.1 Real-time ray tracing. Real-time ray tracing is expected to become more prevalent in the coming years. As hardware-accelerated ray tracing becomes more widespread, we can expect to see even more realistic lighting and reflections in real-time graphics. This will enable the creation of more immersive virtual environments and enhance the visual fidelity of games and other interactive applications. 12.1.4.2 Machine learning in computer graphics. Machine learning techniques are increasingly being used in computer graphics to improve rendering performance and enhance visual quality. Graphics hardware is likely to incorporate dedicated hardware for machine learning tasks, enabling real-time AI-based rendering techniques. This includes applications such as denoising, upscaling, and content generation, where machine learning algorithms can significantly improve the efficiency and quality of the rendering process. 12.1.4.3 Emerging applications of computer graphics. Advancements in graphics hardware will also drive the development of new and innovative applications of computer graphics. This includes areas such as virtual reality, augmented reality, and mixed reality, where realistic and immersive graphics are crucial for creating convincing virtual worlds. Graphics hardware will continue to evolve to meet the demands of these emerging technologies, enabling more seamless and immersive experiences. In conclusion, advancements in graphics hardware have played a pivotal role in the evolution of computer graphics. The increased computational power and specialized capabilities of modern GPUs have enabled the development of more realistic and visually stunning graphics. With the continued advancements in graphics hardware, we can expect even more exciting developments in the field of computer graphics, pushing the boundaries of what is possible in terms of visual fidelity and rendering performance. 12.2 Real-time ray tracing. Real-time ray tracing is a cutting-edge technique in computer graphics that has gained significant attention in recent years. It offers a more realistic and accurate rendering of scenes by simulating the behavior of light rays in a virtual environment. Unlike traditional rasterization techniques, which approximate the interaction of light and surfaces, ray tracing traces the path of individual rays of light as they interact with objects in the scene. This approach allows for more accurate rendering of shadows, reflections, refractions, and other complex lighting effects. 12.2.1 Introduction to real-time ray tracing. Ray tracing has been used in computer graphics for many years, but until recently, it was primarily used in offline rendering applications due to its computational complexity. Real-time ray tracing, on the other hand, aims to achieve interactive frame rates, typically 30 frames per second or higher, making it suitable for real-time applications such as video games, virtual reality, and augmented reality. The basic principle behind ray tracing is to simulate the behavior of light rays by tracing their paths from the camera through each pixel of the image plane and into the scene. For each pixel, a primary ray is cast into the scene, and it interacts with objects by bouncing off surfaces, creating secondary rays that can generate reflections, refractions, and shadows. By recursively tracing these rays, the entire scene can be rendered with accurate lighting and shading. 12.2.2 Ray Tracing Algorithms. Real-time ray tracing requires efficient algorithms to trace rays and calculate their intersections with objects in the scene. Several algorithms have been developed to accelerate ray tracing and make it feasible for real-time applications. These algorithms include 12.2.2.1 Bounding Volume Hierarchy (BVH). BVH is a spatial data structure that organizes objects in the scene into a hierarchy of bounding volumes, such as axis-aligned bounding boxes (AABBs) or spheres. The hierarchy allows for efficient traversal of rays by quickly discarding objects that are not intersected by the ray. BVH construction algorithms, such as the surface area heuristic (SAH), aim to create an optimal hierarchy that minimizes the number of ray-object intersections. 12.2.2.2 KD tree. A KD tree is another spatial data structure that partitions the scene into axis-aligned planes, dividing objects into two subsets at each level of the tree. This hierarchical structure allows for efficient ray traversal by quickly determining which side of the plane the ray intersects and recursively traversing the corresponding subset of objects. KD trees can be constructed using various algorithms, such as the median split or surface area heuristic. 12.2.2.3 Ray-sphere intersection. Ray-sphere intersection is a fundamental operation in ray tracing that determines whether a ray intersects a sphere and calculates the intersection point in normal. This operation is used in various ray tracing algorithms, such as shadow ray casting and refraction calculations. Efficient algorithms, such as the geometric method or the algebraic method, can be used to compute ray-sphere intersections. 12.2.3 Implementation of real-time ray tracing. Implementing real-time ray tracing requires a combination of efficient algorithms, data structures, and hardware acceleration techniques. Modern graphics processing units (GPUs) have evolved to support ray tracing through specialized hardware units, such as ray tracing cores or ray tracing acceleration structures. These hardware advancements enable real-time ray tracing by offloading the computational workload from the CPU to the GPU. To implement real-time ray tracing, developers need to design a ray tracing pipeline that includes stages for ray generation, intersection testing, shading, and output generation. The pipeline starts with generating primary rays for each pixel on the image plane and traversing the scene's acceleration structure to find the closest intersection points. Once an intersection is found, shading algorithms calculate the color and lighting contributions at that point. Finally, the resulting colors are combined and output to the screen. 12.2.4 Performance considerations in real-time ray tracing. Real-time ray tracing is computationally demanding, and achieving interactive frame rates requires careful optimization techniques. Some performance considerations in real-time ray tracing include 12.2.4.1 Acceleration structures. Efficient acceleration structures, such as BVH or KD trees, are crucial for reducing the number of ray-object intersections and improving performance. The construction and traversal algorithms should be optimized to minimize memory access and maximize parallelism. 12.2.4.2 Ray traversal techniques. Efficient ray traversal techniques, such as stackless traversal or packet traversal, can significantly improve performance by reducing memory access and branching overhead. These techniques aim to maximize the coherence of ray traversal and exploit the parallelism of modern GPUs. 12.2.4.3 Shading optimization. Shading calculations can be computationally expensive, especially for complex materials and lighting models. Techniques such as deferred shading, where shading calculations are deferred until after intersection testing, can help reduce the overall shading workload and improve performance. 12.2.4.4 Hardware acceleration. Modern GPUs with dedicated ray tracing hardware can greatly accelerate real-time ray tracing. Developers should leverage hardware features, such as ray tracing cores or ray tracing acceleration structures, to offload the computational workload and achieve real-time performance. Real-time ray tracing represents a significant advancement in computer graphics, enabling more realistic and immersive visual experiences. As hardware and software continue to evolve, real-time ray tracing is expected to become more accessible and widely adopted in various applications, including gaming, virtual reality, and architectural visualization. 12.3 Machine learning in computer graphics. Machine learning has emerged as a powerful tool in various fields, and computer graphics is no exception. With its ability to analyze and learn patterns from large datasets, machine learning has the potential to revolutionize the way we approach optimization techniques in computer graphics. In this section, we will explore the application of machine learning in frustum culling and occlusion culling, two important optimization techniques in computer graphics. 12.3.1 Frustum culling with machine learning. Frustum culling is a technique used to determine which objects in a scene are visible within the camera's view frustum. Traditionally, frustum culling involves performing geometric calculations to determine if an object is inside or outside the frustum. However, this approach can be computationally expensive, especially in scenes with a large number of objects. Machine learning offers an alternative approach to frustum culling by leveraging the power of neural networks. By training a neural network on a dataset of labeled objects, the network can learn to predict whether an object is visible or not based on its position, orientation, and other relevant features. This trained network can then be used to quickly determine the visibility of objects in real-time rendering. The training process involves feeding the neural network with a large dataset of objects along with their visibility status. The network learns to recognize patterns and correlations between the object's properties and its visibility. Once trained, the network can make predictions on new objects, allowing for efficient frustum culling without the need for complex geometric calculations. One of the advantages of using machine learning for frustum culling is its ability to adapt to different scenes and camera configurations. Traditional frustum culling techniques rely on predefined rules and assumptions, which may not always be accurate or optimal. Machine learning, on the other hand, can learn from a diverse range of scenes and adapt its predictions based on the specific context. 12.3.2 Occlusion culling with machine learning. Occlusion culling is a technique used to determine which objects in a scene are occluded or hidden from view by other objects. Traditional occlusion culling algorithms involve performing visibility tests between objects to determine if one object is occluded by another. However, these algorithms can be computationally expensive, especially in scenes with complex geometry. Machine learning can offer a more efficient approach to occlusion culling by learning to predict occlusion based on the properties of objects and their relationships in the scene. By training a neural network on a dataset of labeled occlusion information, the network can learn to recognize patterns and make accurate predictions about occlusion. The training process for occlusion culling involves providing the neural network with a dataset of objects along with their occlusion status. The network learns to identify features and relationships that indicate occlusion, allowing it to predict occlusion for new objects in real-time rendering. One of the key advantages of using machine learning for occlusion culling is its ability to handle complex scenes with dynamic objects. Traditional occlusion culling techniques often struggle with scenes that have moving objects or changing occlusion relationships. Machine learning can adapt to these dynamic scenes by continuously learning and updating its predictions based on new data. 12.3.3 Benefits and challenges of machine learning in culling techniques. The application of machine learning in frustum culling and occlusion culling brings several benefits to the field of computer graphics. Firstly, machine learning can significantly reduce the computational cost of these optimization techniques, allowing for real-time rendering of complex scenes. By replacing complex geometric calculations with learned predictions, machine learning enables faster and more efficient culling. Secondly, machine learning can improve the accuracy of culling techniques by learning from large datasets. Traditional culling algorithms rely on predefined rules and assumptions, which may not always capture the complexity of real-world scenes. Machine learning, on the other hand, can learn from diverse data and adapt its predictions based on the specific context, leading to more accurate culling decisions. However, there are also challenges associated with the application of machine learning in culling techniques. One of the main challenges is the need for large and diverse training datasets. Machine learning algorithms require a significant amount of labeled data to learn effectively. Creating such datasets for culling techniques can be time-consuming and may require manual labeling of objects and their visibility or occlusion status. Another challenge is the interpretability of machine learning models. Traditional culling techniques often rely on geometric calculations that can be easily understood and debugged. In contrast, machine learning models are often considered black boxes, making it difficult to understand why a certain prediction was made. This lack of interpretability can make it challenging to diagnose and fix issues in the culling process. Despite these challenges, the application of machine learning in frustum culling and occlusion culling holds great promise for the future of computer graphics. As machine learning techniques continue to advance and datasets become more readily available, we can expect to see further improvements in the efficiency and accuracy of culling techniques, ultimately leading to more realistic and immersive computer graphics experiences. 12.4 Emerging applications of computer graphics. Computer graphics has come a long way since its inception, and its applications continue to expand into new and exciting areas. In this section, we will explore some of the emerging applications of computer graphics that are shaping the future of various industries. 12.4.1 Virtual Reality (VR). Virtual reality (VR) is a technology that immerses users in a simulated environment, allowing them to interact with and explore virtual worlds. Computer graphics plays a crucial role in creating realistic and immersive VR experiences. By leveraging advanced rendering techniques, such as real-time ray tracing and high-resolution textures, VR applications can transport users to virtual environments that are indistinguishable from the real world. From gaming and entertainment to training simulations and architectural visualization, VR is revolutionizing how we interact with digital content. 12.4.2 Augmented Reality (AR). Augmented reality (AR) overlays digital content onto the real world, enhancing our perception and interaction with the environment. Computer graphics is essential in seamlessly integrating virtual objects into the real world, making them appear as if they exist in the physical space. AR applications rely on techniques like object tracking, depth sensing, and real-time rendering to create convincing and interactive augmented experiences. From industrial maintenance and medical training to retail and education, AR is transforming various industries by providing users with real-time information and interactive digital content. 12.4.3 Medical Visualization. Computer graphics has found extensive applications in the field of medical visualization. From anatomical modeling and surgical simulations to patient education and diagnostic imaging, computer-generated graphics enable healthcare professionals to visualize complex medical data in a more intuitive and informative manner. By leveraging techniques like volume rendering, surface reconstruction, and virtual endoscopy, medical visualization tools can provide detailed and interactive representations of the human body, aiding in diagnosis, treatment planning, and medical research. 12.4.4 Architectural Visualization. Architectural visualization has greatly benefited from advancements in computer graphics. Architects and designers can now create highly realistic and immersive visualizations of their designs, allowing clients and stakeholders to experience and evaluate architectural projects before they are built. With techniques like global illumination, physically based rendering, and virtual walkthroughs, computer graphics enables the creation of photorealistic renderings and interactive virtual tours. This not only enhances the design process but also helps in marketing and communication by providing a compelling visual representation of architectural concepts. 12.4.5 Automotive Design and Simulation. Computer graphics plays a vital role in the automotive industry, particularly in the design and simulation of vehicles. By utilizing techniques like computer-aided design (CAD), virtual prototyping, and physics-based simulations, automotive designers and engineers can visualize and evaluate the performance, aerodynamics, and safety of vehicles in a virtual environment. Computer graphics enables the creation of realistic vehicle models, accurate physics simulations, and visually stunning renderings, helping in the development of safer, more efficient, and aesthetically pleasing automobiles. 12.4.6 Entertainment and Animation. Computer graphics has long been a cornerstone of the entertainment industry, enabling the creation of visually stunning movies, video games, and animated content. With advancements in rendering techniques, animation tools, and motion capture technology, computer graphics has revolutionized the way stories are told and characters are brought to life. From realistic visual effects and lifelike character animations to immersive virtual worlds and interactive gaming experiences, computer graphics continues to push the boundaries of entertainment and captivate audiences worldwide. 12.4.7 Data Visualization. Data visualization is an emerging field that leverages computer graphics to represent complex datasets in a visual and intuitive manner. By using techniques like information visualization, scientific visualization, and interactive data exploration, computer graphics enables the creation of interactive charts, graphs, and visual representations of data. This helps in understanding patterns, trends, and relationships within the data, facilitating data-driven decision-making in various domains, including finance, healthcare, and business analytics. 12.4.8 Simulation and Training. Computer graphics is extensively used in simulation and training applications across various industries. From flight simulators and military training to virtual surgery and disaster preparedness, computer-generated graphics enable realistic and immersive training experiences. By simulating real-world scenarios and environments, computer graphics allows trainees to practice and refine their skills in a safe and controlled setting. This not only enhances learning and skill development but also reduces costs and risks associated with real-world training. 12.4.9 Scientific Visualization. Scientific visualization utilizes computer graphics to represent complex scientific data, enabling researchers to gain insights and communicate their findings effectively. By employing techniques like volume rendering, flow visualization, and molecular visualization, computer graphics helps in visualizing and analyzing data from various scientific disciplines, including astronomy, geology, biology, and physics. This aids in understanding complex phenomena, identifying patterns, and communicating scientific concepts to a wider audience. 12.4.10 Advertising and Marketing. Computer graphics has become an integral part of advertising and marketing campaigns. By leveraging techniques like 3D modeling, animation, and visual effects, computer graphics enables the creation of visually compelling and attention-grabbing advertisements. From product visualizations and virtual showrooms to interactive displays and augmented reality experiences, computer graphics helps in creating engaging and immersive marketing content that captivates consumers and drives brand awareness. In conclusion, computer graphics has evolved beyond traditional applications and is now driving innovation in various industries. From virtual reality and augmented reality to medical visualization and automotive design, computer graphics is transforming the way we interact with digital content and shaping the future of numerous fields. As technology continues to advance, we can expect even more exciting and groundbreaking applications of computer graphics in the years to come.